Picture a place where reality itself bends and breaks, a point in space where the very laws that govern our universe cease to function. This is the edge of a black hole, a boundary known as the event horizon, a one-way door from which not even light can escape. It's a realm of pure, unimaginable gravitational force, and at its very heart lies the greatest cosmic puzzle of all, the singularity. We're about to explore 30 of the most profound and perplexing unsolved mysteries surrounding black holes and singularities, questions that push the very limits of human knowledge and challenge our fundamental understanding of physics. These are not just abstract curiosities, they are the frontier of our comprehension, the places where our current science reaches its end and pure wonder begins. Every one of these mysteries represents a crack in the foundation of our cosmic worldview, and by investigating them, we are not just learning about distant regions of space, we are fundamentally exploring the nature of reality itself. Think about the sheer audacity of what we are trying to comprehend. A singularity is a point of infinite density, a place where the mass of a star millions of times heavier than our Sun is crushed into a space smaller than a single atom. The mathematics tells us that here, space and time as we know them simply come to an end. What does that even mean? How can something be infinite? This isn't just a difficult scientific problem. It's a philosophical and existential one that touches on the very fabric of existence. The journey to understand these cosmic anomalies is a story of human ambition and curiosity, a testament to our relentless drive to look into the deepest, darkest corners of the universe and demand answers. It connects us to every explorer and thinker who has ever gazed at the night sky and dared to ask what lies beyond. This video is your invitation to stand at that precipice with us. We will journey together through the most baffling questions that keep physicists and astronomers awake at night. We will grapple with the paradoxes that seem to defy logic, from the terrifying fate of anything that crosses the event horizon to the potential that black holes might be gateways to other universes or even the ultimate key to a grand unified theory of everything. This isn't a dry lecture, it's an expedition to the very edge of understanding, a deep dive into the unknown that promises to reshape how you see the cosmos. So let's begin this exploration, one magnificent and terrifying mystery at a time. And so we arrive at our first and perhaps most fundamental mystery, the very core of the enigma. What exactly is a singularity? When we talk about the heart of a black hole, we are not discussing a solid surface or a swirling vortex of matter in the traditional sense. Instead, general relativity predicts a point of zero volume and infinite density, a place where the very fabric of spacetime is curved to an infinite degree. The equations tell us that all the matter that ever fell into the black hole gets crushed into this single, dimensionless point. The concept of here and now loses all meaning, and the laws of physics as we know them simply cease to apply. This is not just an extreme environment, it is the complete and utter breakdown of our current understanding of the universe. The word singularity literally means a point where our mathematical models fail, and it could not be a more fitting term. This presents a monumental problem for physicists. Is this infinite point a real physical object that exists out there in the cosmos? Or is it merely a glaring signal that Einstein's theory of general relativity, while brilliant and incredibly accurate everywhere else, is incomplete? Think of it like a calculator being asked to divide by zero. The machine gives you an error not because the concept is philosophically impossible, but because it has reached the limit of its operational framework. In the same way, the singularity might be the point where our calculator, the mathematics of general relativity, hits its own divide by zero moment. The prevailing hope is that a unified theory of quantum gravity, one that successfully marries the vast cosmic scales of relativity with the bizarre probabilistic world of quantum mechanics, will step in to resolve this infinity. Such a theory might reveal that the singularity is not a true infinity, but rather a fantastically dense yet finite state of matter governed by quantum laws we have yet to discover. But for now, in the absence of that ultimate theory, the singularity remains the ultimate unknown, a profound question mark at the center of our most mysterious cosmic objects. It is the ultimate frontier, a place where our knowledge ends and pure, unadulterated mystery begins. Building directly on the terrifying concept of the singularity, we encounter a puzzle that is just as profound but operates on an entirely different, almost ethereal level. This is the information paradox, a problem so significant that it caused its originator, the legendary Stephen Hawking, to fundamentally rethink his own ideas and even concede a famous bet. At its heart, this mystery isn't about the fate of matter or energy, but about something far more abstract: information. In our everyday world, information is the blueprint of a thing. If you were to burn a book, the paper and ink are transformed into ash and smoke. But in principle, if you could collect every single particle of that smoke and ash and track the precise energy released, you could theoretically reconstruct the entire book. Every word, every punctuation mark would be recoverable. This principle is a cornerstone of quantum mechanics, the law of the conservation of quantum information. It states that information can never be truly destroyed. It can only be scrambled, transformed, or hidden. Now, imagine throwing that book into a black hole. For decades, physicists thought the story was simple. The book crosses the event horizon, is torn apart, and its remains are crushed into the singularity. According to Einstein's general relativity, the book and all the information it contained is gone forever from our universe, locked behind a one-way membrane. This, however, is where Hawking made his revolutionary discovery. He realized that black holes aren't completely black. Due to weird quantum effects happening just outside the event horizon, black holes slowly leak radiation, now famously known as Hawking radiation. This process causes the black hole to gradually lose mass and, over astronomical timescales, evaporate completely. Here lies the paradox. Hawking's initial calculations suggested that this Hawking radiation is completely random and thermal. It contains no information whatsoever about what fell into the black hole. It's like the smoke from our burned book carrying not a single trace of the letters or words. So, when the black hole finally evaporates and vanishes in a final puff of this random radiation, what happened to the original quantum information of the book? If it's truly gone, then a fundamental law of the universe has been broken. This created a crisis in physics, often summed up as the phrase, "it from bit." If the information about things, the bits, can be lost, then the very existence of those things, the its, becomes precarious. The debate that followed split the physics community for years. One camp, initially led by Hawking, argued that information really is destroyed and that quantum mechanics must be modified. The other camp, including many other prominent theorists, insisted that information must be preserved and that the problem lay with our understanding of Hawking radiation or the event horizon. This led to some truly mind-bending proposed solutions. One compelling idea is that the information isn't lost inside the black hole, but is somehow encoded or painted onto the two-dimensional surface of the event horizon itself. In this holographic principle, our three-dimensional reality of the book falling in is preserved as a scrambled, two-dimensional projection on the horizon surface, and this information is then slowly and subtly encoded into the Hawking radiation as the black hole evaporates. Another, even more dramatic proposal is the notion of firewalls. If information is to escape, perhaps the event horizon isn't the smooth gateway general relativity describes, but is instead a searing wall of high-energy particles that violently incinerates anything that comes into contact with it, simultaneously releasing the information back out. This solution, however, creates its own paradox by violating Einstein's principle that an astronaut crossing the event horizon should notice nothing special. The information paradox forces us to choose between cherished principles, pitting quantum mechanics against general relativity in a direct confrontation, and the resolution, when it comes, will undoubtedly reshape our understanding of reality at its most fundamental level. This startling proposal, known as the Firewall paradox, catapults the information paradox from a theoretical debate into a violent and dramatic confrontation. The idea emerged when physicists attempted to rigorously enforce the conservation of quantum information. If the Hawking radiation leaking from a black hole must carry out the information of what fell inside, then a profound consequence seems unavoidable. For the information to escape, the intricate quantum connections or entanglement between particles just inside the event horizon and particles just outside must be severed. This severing, however, would release an enormous amount of energy. The result, the placid event horizon envisioned by Einstein's theory, would transform into a seething, lethal barrier, a literal firewall of intense radiation that would vaporize anything attempting to cross it. This immediately creates a devastating conflict with one of the bedrock principles of general relativity, the equivalence principle. This principle states that if you are in free fall, you should feel weightless and should not be able to detect any local difference when you pass through the event horizon. There should be no dramatic sign, no special ribbon-cutting ceremony marking your one-way trip. If you were falling into a stellar mass black hole, you would cross the event horizon without even noticing it. The firewall scenario shatters this elegant picture. Instead of a silent, invisible boundary, you would encounter the most energetic wall of fire imaginable long before reaching the point of no return. The astronaut in our thought experiment wouldn't be gracefully stretched into spaghetti by tidal forces. They would be instantly and utterly incinerated into a cloud of fundamental particles. So we are left with a seemingly impossible choice, a trilemma where all three options appear necessary, yet they cannot all be true. First, we want to preserve the equivalence principle, which says the event horizon should be uneventful. Second, we demand that the laws of quantum mechanics hold, meaning information cannot be lost. And third, we assume that physics operates consistently everywhere, a concept known as locality. The firewall argument forces us to abandon one of these three cherished ideas. Either we give up on the equivalence principle and accept the fiery death of an astronaut, we allow quantum information to be permanently destroyed, or we reconsider our most basic assumptions about how cause and effect operate in the universe. Each of these options feels like a defeat, a sign that our understanding is fundamentally flawed. The firewall is not so much a solution as it is a stark warning, a bright flashing sign that says the conflict between general relativity and quantum mechanics is not just a minor technicality but a deep, foundational crisis that demands a revolution in physics. It shows us that when our two most powerful descriptions of reality collide, the consequences are not just mathematically messy, they are literally explosive. Having grappled with the paradoxical fate of information at the event horizon, we now take the ultimate plunge, crossing that threshold into the greatest uncharted territory in the cosmos. What actually lies inside a black hole? This is a mystery defined by pure, exhilarating speculation, because the fundamental rule of these objects that no information can escape places a permanent keep-out sign on the universe's most fascinating frontier. We are left with the powerful but incomplete maps provided by mathematics, which paint wildly different pictures of the interior. The simplest model, based on a non-rotating black hole, suggests a harrowing journey. Once you cross the event horizon, every path leads inexorably inward toward the central point singularity. There is no stopping, no turning back. Space itself is flowing faster than light toward that central point, dragging you along with it. The tidal forces would stretch you into a long, thin strand of atoms in a process poetically known as spaghettification, before you are ultimately crushed into the singularity itself. It's a one-way trip to a destructive end, but our universe is dynamic and full of spin, and most black holes are thought to be rotating, described by the more complex Kerr solution. This changes the interior from a terrifyingly simple death trap into a landscape of breathtaking possibility. In a rotating Kerr black hole, the point singularity transforms into a ring, a one-dimensional loop of unimaginable density. This ring singularity is not just a different shape, it's a potential gateway. The mathematics suggests that if you could navigate the intense, chaotic forces inside, you might actually pass through the ring without being destroyed. And what lies on the other side? The equations don't end there. They open up into a mirrored region of space-time called an anti-universe, or even a hypothetical passageway known as an Einstein-Rosen bridge, a wormhole. This theoretical tunnel could connect two distant points in our own universe, or even more fantastically, serve as a bridge to an entirely separate universe altogether. You wouldn't be crushed, you would be transported. This leads to some of the most profound speculation in all of physics. Could black holes be the creators of new universes? Some cosmological models suggest that the infinitely dense state at the center of a black hole could trigger a new Big Bang, giving birth to an entirely new cosmos with its own laws of physics, bubbling into existence in a hidden dimension separate from our own. In this mind-bending scenario, our entire universe might itself reside inside a black hole that is part of a much larger meta-universe. This idea, sometimes called cosmological natural selection, posits that universes reproduce through their black holes, with each new universe having slightly different physical constants. The black holes we observe could be cosmic wombs, and we, living inside one of their offspring, are simply unaware of our own origins. Yet, for all these breathtaking theories, the brutal, fundamental truth remains: we cannot know. Every one of these models, the destructive point, the gateway ring, the baby universe, exists purely in the realm of mathematics and thought experiments. The cosmic censorship hypothesis, a conjecture proposed by Roger Penrose, suggests that nature abhors a naked singularity and always hides it behind an event horizon, precisely to prevent the unpredictable physics at the singularity from affecting our orderly universe. This cosmic curtain ensures that the deepest secrets of black holes are permanently locked away from our view. The interior of a black hole is the ultimate sealed room mystery. We can deduce what might be happening based on the clues left outside, but the door is permanently shut and the key is lost inside. This makes the question of what's inside a black hole more than just a physics problem. It is a permanent monument to the limits of human knowledge, a reminder that some frontiers may forever remain in the glorious, tantalizing realm of the unknown. This journey past the event horizon inevitably leads us to the most intimate and terrifying of all the black hole's mysteries, the ultimate fate of the matter that makes the trip. We've discussed the bizarre physics of the horizon and the enigmatic singularity, but what actually happens to a star, a spacecraft, or a person in the final moments? The classic and most widely accepted answer is a process as dramatic as its name: spaghettification. Imagine the gentle pull of the moon creating our ocean tides. Now amplify that difference in gravitational pull to an almost infinitely violent degree. As an object approaches the central point of a black hole, the force of gravity on the side closest to the singularity is astronomically stronger than the force on the far side. This incredible tidal force doesn't just pull, it stretches. An astronaut falling feet first would feel their feet accelerating so much faster than their head that their entire body would be elongated into a long, thin stream of atoms resembling a piece of spaghetti. Every molecule, every atom would be pulled apart in this cosmic tug-of-war, creating a thin, hot stream of elementary particles racing toward their final destination. Conventional wisdom states that this stream of particles then impacts the singularity, where, according to the equations of general relativity, it is crushed into a point of infinite density. It ceases to be matter as we know it and simply becomes part of the singularity's infinite curvature. its information and structure seemingly erased from existence forever. But what if that crushing finale isn't the only possible outcome? What if the singularity isn't an end but a transformation? This is where the theories become truly spectacular. One of the most captivating ideas arises from the mathematics of the maximally extended Schwarzschild solution, which describes a theoretical object known as a white hole. If a black hole is a region of space from which nothing can escape, a white hole is its exact opposite, a region of space into which nothing can enter. It is a point of pure, violent ejection, spewing out matter and energy relentlessly. Some physicists have proposed that the tunnel-like interior of a black hole, an Einstein-Rosen bridge, might not connect back to our own universe but could instead terminate as a white hole in an entirely different universe or a distant part of our own. In this breathtaking scenario, the matter that gets spaghettified isn't destroyed at all. After its harrowing journey through the black hole's interior, it is violently flung out of the white hole, becoming the raw material for a new region of spacetime. You wouldn't be annihilated, you would be reborn, albeit in a form and a place we cannot possibly imagine. An even more profound possibility is that the matter falling into a black hole becomes the seed for an entirely new cosmos. This idea, closely associated with theorists like Lee Smolin, is known as the theory of cosmological natural selection or the fecund universe theory. It posits that the extreme conditions at the singularity, effectively a reversal of the conditions we see in the expanding universe, trigger a new Big Bang. When matter is crushed to that incredible density, the laws of physics as we know them break down, potentially allowing for a new set of physical constants to snap into place. The black hole in our universe would then be the birthplace of an entirely new, separate universe, bubbling into existence in its own dimensional space. In this view, every star that collapses into a black hole isn't a death but a genesis. The matter that falls in provides the fundamental ingredients for a new reality, with its own stars, galaxies, and potentially, its own black holes giving birth to even more universes. This creates a grand, cosmic evolutionary tree where universes that produce more black holes are fitter, as they produce more offspring. The haunting and beautiful implication is that our entire universe, with its perfect conditions for life, might itself be the interior of a black hole that formed in a larger parent universe. These radical theories force us to confront the very limits of what we mean by existence. Is the destruction of information at a singularity truly an end, or is it a transformation so complete that it constitutes a new beginning? We are left oscillating between two terrifying and magnificent visions. In one, matter meets a definitive and absolute end, crushed out of existence in a realm where time and space cease to have meaning. In the other, matter is immortal, perpetually recycled through cosmic gateways to fuel an infinite fractal of new realities. The fate of matter inside a black hole is more than a physics puzzle. It is the ultimate question of endings and beginnings, a mystery that lies at the precipice of science, philosophy, and the human imagination. From the chaotic interior of a black hole, we are now drawn to a theoretical possibility, even more unsettling, a singularity completely exposed to the wider universe. This is the concept of a naked singularity, a gravitational monster without its protective cloak, an infinitely dense point with no event horizon to shield the cosmos from its unpredictable physics. Imagine a place where the laws of the universe break down, but this time its bizarre and lawless effects are not locked away. They could, in principle, be observed, touched, and could even influence our reality directly. The equations of Einstein's general relativity do not explicitly forbid such an object. Under certain specific conditions, such as the collapse of a cloud of dust with a perfectly symmetrical shape or the rapid rotation of an exceptionally massive star, the mathematics suggests that an event horizon might not form, leaving the raw singularity bare for all to see. This prospect was so troubling to the renowned physicist Roger Penrose that he formulated the cosmic censorship hypothesis, a bold conjecture that nature herself abhors such a spectacle. Penrose proposed that a fundamental, yet undiscovered, law of physics always steps in to prevent a naked singularity from forming. In this view, whenever a singularity is created during gravitational collapse, an event horizon must always form around it, acting as a cosmic curtain that protects the sensible, predictable universe from the chaotic and unknown physics at the singularity. It is a statement of cosmic decorum, ensuring that the wild west of infinite density is always fenced off from the well-ordered town of our observable cosmos. But why are physicists so deeply wary of a naked singularity? The fear stems from the complete breakdown of predictability. Within the singularity, the known laws of physics, including Einstein's equations, cease to function. Space and time themselves lose their meaning. If such a point were visible and accessible, its influence would radiate outward. The most sacred principle in all of physics, causality, the idea that a cause must always precede its effect, could be shattered. In the presence of a naked singularity, it might be possible to have closed time-like curves, which are essentially paths through space-time that loop back on themselves. An astronaut traveling on such a path could theoretically meet their younger self or even prevent their own birth, creating paradoxes that defy logic and our entire understanding of a coherent universe. The predictable flow of time, the very foundation upon which we build our science and our experience of reality, would become unmoored. Consequently, the search for, or definitive proof against, the existence of naked singularities has become one of the most critical tests for our theories of gravity. If astronomers were to ever detect an object that behaved like a black hole but lacked an event horizon, it would be a monumental discovery, forcing an immediate revision of general relativity and providing the first direct glimpse into the realm of quantum gravity. Conversely, if continued observations and theoretical work consistently show that singularities are always hidden, it would provide powerful indirect support for the cosmic censorship hypothesis and reinforce our current understanding. This mystery sits at a fascinating crossroads, compelling us to ask whether the universe possesses an innate sense of order, a built-in mechanism that prevents its own deepest secrets from causing cosmic chaos, or whether we are simply fortunate that such terrifying objects have not yet revealed themselves in our celestial neighborhood. Shifting our focus from the theoretical dangers of singularities, we encounter a colossal mystery that is very real and observed throughout the cosmos: the enigma of the supermassive black holes that anchor the centers of galaxies. These are not the stellar mass black holes formed from a single dying star. These are true leviathans, weighing in at millions or even billions of times the mass of our Sun, and their very existence so early in the universe presents a monumental challenge to our understanding of cosmic history. The puzzle is one of time. We have observed fully formed supermassive black holes shining brightly as quasars when the universe was less than 1 billion years old, a mere blink of an eye in cosmic terms. For a black hole to grow to billions of solar masses that quickly, it would have to consume matter at a ferocious, nearly uninterrupted rate, pushing against fundamental limits set by physics itself. This creates a chicken-and-egg problem on a galactic scale. Which came first, the galaxy or the giant black hole at its heart? And just how did these monsters get their start? Theories for their origin revolve around the nature of the initial seed from which they grew. One leading idea is that the first generation of stars, known as population 3 stars, were behemoths hundreds of times more massive than our Sun. When these titanic stars reached the end of their brief lives, they would have collapsed directly into black holes of perhaps a few hundred solar masses. These black holes then sank to the center of the nascent galaxy and began a long, slow feast, merging with others and voraciously accreting gas to eventually become the supermassive entities we see today. While this is a plausible path, the timeline is incredibly tight. growing from a few hundred solar masses to several billion in less than a billion years is a staggering feat, requiring perfect conditions and a nearly limitless supply of food. This difficulty has led to the proposal of more exotic seeds. Imagine the direct collapse of an enormous, pristine cloud of primordial gas in the early universe. Without heavy elements to help it cool and fragment into many small stars, such a cloud could collapse monolithically under its own gravity, directly forming a black hole seed with a mass of tens of thousands or even 100,000 suns right from the outset. This so-called direct collapse black hole would give growth a monumental head start, making the rapid ascent to supermassive status far more feasible. It's the difference between planting a sapling and planting a fully grown tree. The latter reaches its ultimate height much faster. Perhaps the most exotic possibility of all is that the seeds for these giants were not stellar in origin at all, but primordial. In the incredibly dense and chaotic first moments after the Big Bang, random fluctuations in density could have been so extreme that pockets of space simply collapsed under their own weight, forming black holes of all sizes. These primordial black holes would have been woven into the fabric of the cosmos from its very beginning. A handful of these that were large enough could have served as the ready-made kernels around which the first galaxies assembled, providing a pre-built foundation for the supermassive black holes we find today. This idea elegantly solves the timing problem, but it remains highly speculative, as we have yet to find definitive evidence that primordial black holes actually exist. What's become increasingly clear is that these central black holes are not passive occupants. They are active participants in the life of their galaxies. The energy they release as they feed can heat surrounding gas, regulate star formation, and even drive powerful winds that shape the galaxy's evolution. This intricate cosmic dance between the growth of the black hole and the growth of its host galaxy suggests a profound and fundamental connection that we are only just beginning to understand. The mystery of the supermassive black hole's origin is therefore not an isolated curiosity. It is a key that unlocks the story of how the largest structures in our universe came to be, forcing us to question our most basic timelines and mechanisms for cosmic construction. This mysterious connection between the supermassive black hole and its host galaxy presents one of the most compelling puzzles in modern astronomy, a cosmic relationship that seems to defy scale. How can an object that constitutes a mere fraction of a percent of a galaxy's total mass, a tiny speck at the center, somehow hold such sway over the entire system? The clues to this symbiosis began to emerge when astronomers noticed a stunning correlation, now known as the M-sigma relation. This isn't just a loose association. It's a remarkably tight mathematical link between the mass of the central supermassive black hole and the velocity dispersion of the stars in the galaxy's central bulge. In simpler terms, the faster the stars are whizzing around the galactic center, the more massive the black hole tends to be. This correlation is too precise to be a coincidence, strongly suggesting that the growth of the black hole and the evolution of its host galaxy are fundamentally intertwined, like two dancers in a cosmic ballet whose movements are perfectly synchronized over billions of years. The question then becomes, who is leading this dance? Does the galaxy shape the black hole, or does the black hole control the galaxy? The most widely accepted explanation points to the incredible power unleashed when the black hole actively feeds. During these periods, known as active galactic nuclei or quasar phases, the infalling matter releases a phenomenal amount of energy as light, heat, and radiation. But the most dramatic influence comes from the colossal jets that often erupt from the poles of the spinning black hole. These are not gentle streams, they are relativistic beams of charged particles shooting across thousands of light years, slamming into the galaxy's reservoir of cold gas, the very raw material needed to form new stars. This process, aptly named quasar feedback, acts as a cosmic thermostat. When star formation becomes too vigorous, it funnels gas toward the center, feeding the black hole and igniting a powerful outburst. The resulting jets and radiation then heat and blow away the surrounding gas, effectively shutting down star formation and putting the galaxy on a diet. It's a self-regulating cycle where the black hole, once thought to be a passive destroyer, becomes an active governor, preventing the galaxy from growing too large too quickly and explaining the observed mass correlation. Yet, some scientists wonder if this energetic feedback is the whole story. Could there be a deeper, more fundamental link established during the galaxy's very formation? Perhaps both the galaxy and its central black hole grew from the same initial seed of dark matter, their fates written into the cosmic blueprint from the very beginning. In this view, the gravitational pull of the dark matter halo that defines the galaxy also dictates how much gas flows to the center, naturally setting the maximum size for both the stellar bulge and the black hole. Their growth would be parallel processes choreographed by the underlying dark matter scaffold, with the black hole's feedback acting more as a fine-tuning mechanism than the primary conductor. This idea suggests the correlation we see is a fossil record of their shared origin, a bond forged in the fiery crucible of the early universe that has persisted throughout cosmic time. The implications of this connection are profound, transforming our understanding of galactic life cycles. A galaxy is not a static island of stars. It is a dynamic ecosystem where a hidden engine at its core can dictate its ultimate fate. A supermassive black hole with a strong bout of feedback can effectively quench star formation, leading to the creation of a red and dead elliptical galaxy, full of aging stars but devoid of the fresh gas needed to birth new ones. Without this regulatory influence, a galaxy might continue to form stars in an unchecked frenzy, potentially evolving along a very different path. This intricate interplay demonstrates that the largest structures in the universe and the most extreme objects within them are not independent. They are partners in a grand, co-evolutionary tango that has shaped the visible cosmos we observe today. The black hole galaxy connection is a stunning reminder that even the smallest components can, under the right conditions, hold dominion over the whole, a testament to the complex and surprising ways the universe organizes itself across immense scales. This faint glow, predicted by Stephen Hawking, brings us to a mystery that fundamentally redefined the very nature of these cosmic objects. Hawking radiation is the astonishing idea that black holes are not the perfect eternal prisons we once thought, but are instead slowly leaking energy, fading away over cosmic timescales. The mechanism for this is one of the most elegant and bizarre consequences of marrying quantum mechanics with gravity, and it all hinges on the strange behavior of empty space. Even in a perfect vacuum at the tiniest of scales, space is not truly empty. It is a seething, bubbling foam where pairs of virtual particles constantly blink into and out of existence. These are particle-antiparticle pairs that borrow energy from the universe for an incredibly brief moment, mandated by the Heisenberg uncertainty principle, before they annihilate each other and pay back the energy loan, vanishing as quickly as they appeared. Normally, this quantum frenzy is completely undetectable. It's the background hum of reality with no net effect. But place this quantum activity right at the precipice of a black hole's event horizon and everything changes. Imagine one of these virtual particle pairs spontaneously appearing exactly at the boundary. The intense gravitational energy of the black hole can intervene, ripping the two particles apart before they have a chance to annihilate. In this cosmic robbery, one particle falls into the black hole, while its partner is gifted with real energy from the gravitational field and escapes into space, becoming a genuine particle of radiation. From the perspective of a distant observer, it appears as if the black hole has just emitted a particle. There is, however, a profound cost for this emission. The particle that falls into the black hole must have negative energy relative to the outside universe to conserve overall energy. When this negative energy particle is absorbed, it effectively reduces the total mass energy of the black hole. So, by emitting this faint stream of radiation, the black hole is not just glowing, it is slowly and inexorably losing mass, evaporating particle by particle. This leads to a staggering long-term fate. A stellar mass black hole, due to its immense size, emits Hawking radiation that is incredibly cold, far colder than the cosmic microwave background radiation that fills the universe. For now, such black holes are actually gaining mass from absorbing ambient radiation faster than they evaporate. But in the distant future, trillions upon trillions of years from now, as the universe expands and cools, the tide will turn. These black holes will begin to lose mass, and as they shrink, the process accelerates. A black hole's temperature is inversely proportional to its mass, so as it gets smaller, it gets hotter and radiates faster. In the final, frantic seconds of its multi-trillion-year life, a black hole is predicted to release the energy equivalent of millions of hydrogen bombs in a blinding flash of radiation and particles before vanishing completely. Yet, for a theory that is so foundational to modern physics, we face an immense practical challenge. We have never directly observed Hawking radiation. The problem is one of scale. For a black hole with the mass of our Sun, the Hawking radiation temperature is a minuscule 1/1000th of a degree above absolute zero, making it utterly drowned out by all other cosmic signals. Confirming its existence directly from an astrophysical black hole is currently beyond our technological reach. This has motivated incredibly innovative experiments here on Earth. Scientists have created analogous event horizons in laboratories using supercooled Bose-Einstein condensates or flowing water, where the mathematics governing sound or light waves mimics the physics around a gravitational horizon. In these setups, researchers have detected a form of Hawking radiation in the form of phonons, or sound wave particles, providing strong indirect support for Hawking's brilliant insight. A confirmed direct detection from an actual black hole would be a monumental triumph. It would be the first direct evidence of a quantum gravitational effect, a stunning demonstration that quantum mechanics operates successfully even in the most extreme gravitational fields. It would validate our understanding of quantum field theory in curved spacetime and provide crucial experimental data for any theory of quantum gravity. Furthermore, it would seal the fate of black holes, confirming that they are indeed transient features of our cosmos, destined to eventually evaporate and leave behind only a faint whisper of radiation as their final testament. Hawking radiation is more than just a theoretical curiosity. It is a profound bridge between the very large and the very small, a ghostly signal that whispers the ultimate transformative secret of black holes. Following the logic of Hawking radiation to its ultimate conclusion forces us to confront a truly staggering possibility. Black holes may not be permanent. If they are constantly emitting energy, they must, by the fundamental laws of physics, be losing mass in the process. This leads us to the concept of black hole evaporation, a slow, inexorable decay that unfolds over timescales so vast they defy human comprehension. For a typical stellar mass black hole, say one with the mass of our Sun, the Hawking radiation it emits is incredibly feeble. Its temperature is barely a billionth of a degree above absolute zero, meaning it is actually absorbing more energy from the cosmic microwave background radiation than it is radiating away. In its current state, it's growing, not shrinking, but the universe is expanding and cooling, and in the far, far future, the background temperature of the cosmos will drop to near zero. At that point, the black hole will finally begin to lose mass in earnest. The calculation for how long this takes is humbling. A solar mass black hole would take approximately 10 to the 67 years to evaporate completely. That's a 1 followed by 67 zeros. To put that timescale in perspective, the current age of our entire universe is only about 10 to the 10 years. The lifespan of a typical black hole is to the current age of the universe what the current age of the universe is to the briefest instant you can imagine. This evaporation is not a linear process, it is a runaway reaction. A black hole's temperature is inversely proportional to its mass, so as the black hole loses mass, it gets hotter. As it gets hotter, it radiates energy more intensely. As it radiates more intensely, it loses mass even faster. This creates a positive feedback loop, turning the final stages of evaporation into a crescendo. For almost all of its 10 to the 67-year lifespan, the black hole is a cold, dark, and nearly inert object. But in its last second of existence, when its mass has dwindled to that of a small mountain, its temperature soars to billions of degrees, and it releases a phenomenal burst of high-energy radiation and particles. This final flash would be a brilliant, explosive spectacle, signaling the complete disappearance of a once mighty gravitational giant. It is the ultimate fate for any black hole that isn't continuously fed. But this dramatic finale introduces one of the most vexing questions in theoretical physics. What exactly happens at the very end? The straightforward application of Hawking's original calculation suggests the black hole simply vanishes, and with it, all the information about everything that ever fell inside. This, as we've discussed, violates quantum mechanics. The information paradox reaches its climax at the moment of evaporation. To resolve this, theorists have proposed several breathtaking possibilities for that final instant. One idea is that the evaporation process stops just short of zero, leaving behind a stable, microscopic remnant no heavier than a speck of dust, but containing within it the entire compressed information of the black hole's history. This remnant would be a fossil, a permanent tombstone for the black hole, preserving the universe's quantum ledger for all eternity. Another, even more radical proposal is that the final explosion is not an end but a transformation. Perhaps the evaporating black hole doesn't vanish into nothingness, but instead, at the very moment its mass reaches zero, it opens up, revealing a gateway to another region of space-time, a baby universe. In this scenario, the information isn't lost, it is transferred into this new, separate cosmos, a universe whose own Big Bang was triggered by the death scream of a black hole in our own. This offers a beautiful, if dizzying, solution. The information is preserved, just not in a place we can ever access. The debate over the endpoint of evaporation is far from settled. It represents a frontier where our current theories of gravity and quantum mechanics both break down completely. And until we have a fully realized theory of quantum gravity, the final fate of an evaporating black hole will remain one of the most profound and unresolved mysteries in all of cosmology. This concept of black holes having temperature and slowly evaporating revolutionized our understanding, but it opened the door to an even deeper and more perplexing mystery, one that ties these cosmic objects directly to the most fundamental laws of thermodynamics. We are talking about black hole entropy. At first glance, the idea seems absurd. Entropy is a measure of disorder or the number of ways you can rearrange the microscopic components of a system without changing its overall appearance. Think of a clean room versus a messy room. Both contain the same objects, but the messy room has higher entropy because there are far more ways to arrange the room that still look messy. It's a statistical property of complex systems with many moving parts. A black hole, according to the classic no-hair theorem, is the ultimate simple object. It is described by just three numbers: its mass, its electric charge, and its spin. It has no other features, no complicated structure. It is, in a sense, the most ordered object imaginable. So how could it possibly possess entropy, a property of disorder? The genius of Jacob Bekenstein, a young graduate student at the time, was to propose that it must. His reasoning was based on a fundamental law, the second law of thermodynamics, which states that the total entropy of the universe always increases. Imagine throwing a box of hot, high-entropy gas into a black hole. If the black hole itself had zero entropy, then the total entropy of the universe would appear to decrease. The gas and its disorder would be gone from our observable universe, violating this sacred law. Wittgenstein argued that to save the second law, the black hole must gain entropy itself, an amount proportional to the area of its event horizon. Stephen Hawking initially ridiculed this idea, but his own discovery of Hawking radiation forced him to not only accept it but to refine it. Together, they gave us the Wittgenstein-Hawking formula. A black hole's entropy is exactly 1/4 of the area of its event horizon, measured in Planck units. This is not a small number. A single stellar mass black hole has an entropy that is astronomically larger than the entropy of all the stars, planets, and gas in the entire visible universe combined. A black hole is not a simple object. It is the most entropic object in existence, a reservoir of disorder of almost unimaginable proportions. This leads to the heart of the mystery. In any ordinary system, we know what gives rise to entropy. For that box of gas, it's the countless possible positions and velocities of all the trillions upon trillions of molecules. Each molecule is a degree of freedom, a way for the system to store information and create disorder. But what are the microscopic degrees of freedom for a black hole? What are the individual bits that are being scrambled to produce this unimaginably vast entropy? The Wittgenstein-Hawking formula provides a profound clue. The entropy is proportional to the horizon's area, not the black hole's volume. This is a radical departure from everything else we know. In our everyday world, entropy is an extensive property. If you double the volume of a gas, you double its number of molecules and thus its entropy. But for a black hole, the entropy scales with the surface area. This astonishing fact was a primary inspiration for the holographic principle, the mind-bending idea that all the information describing the three-dimensional volume of a region of space might be entirely encoded on its two-dimensional boundary like a cosmic hologram. The surface of the event horizon appears to hold a pixelated map of everything that fell inside, with each Planck-sized area unit, a square that is an incredibly tiny 10 to the negative 66 centimeters on a side, acting as a single bit of information. The question then becomes, what is the true nature of these pixels? What physical phenomena on the horizon are actually storing this information? String theory, one of the leading candidates for a theory of quantum gravity, offers a compelling picture. It suggests that the event horizon is not a placid, empty surface, but a tangled web of incredibly tiny, vibrating strings. The different vibrational patterns of these fundamental strings could represent the different microscopic states that account for the black hole's entropy. It's as if the horizon is a vast cosmic membrane, and every possible vibration of that membrane corresponds to a different arrangement of all the particles that form the black hole. Other approaches, like loop quantum gravity, propose that space itself is quantized, woven from discrete loops, and that the entanglement of these loops at the horizon creates the vast number of possible states. The mystery of black hole entropy is therefore far more than a curiosity about disorder. It is a direct bridge linking the large-scale physics of gravity and thermodynamics with the microscopic quantum world. Solving it means understanding how space-time itself is built from fundamental quantum bits, and why the universe seems to operate like a hologram, with its deepest secrets painted on a distant, two-dimensional surface. Now we venture into a concept so profound and elegant that it weaves together two of the most baffling phenomena in physics into a single, breathtaking tapestry. This is the ER equals EPR conjecture, an idea that suggests the deepest secrets of black holes and quantum weirdness are two sides of the same cosmic coin. To understand this, we need to look at its two parts. ER stands for Einstein-Rosen bridge, the formal name for a wormhole, a hypothetical tunnel through space-time connecting two distant points. EPR stands for Einstein, Podolsky, and Rosen, the physicists who, in a famous paper, highlighted the bizarre, spooky action at a distance of quantum entanglement, where two particles can be instantaneously connected regardless of the vastness separating them. For decades, these were considered completely separate concepts, one a speculative feature of gravity and general relativity, the other a confirmed but puzzling property of the quantum world. The revolutionary conjecture, most famously championed by physicists Juan Maldacena and Leonard Susskind, proposes that these two ideas are actually equivalent. An Einstein-Rosen bridge and a pair of entangled particles are not just analogous, they are, in some fundamental way, the same thing described in different languages. Let's break down this astonishing claim. Imagine you have two entangled particles, say two electrons. Their properties are linked so that measuring the spin of one instantly determines the spin of the other, even if they are on opposite sides of the galaxy. This connection seems to violate the speed of light limit, a fact that so troubled Einstein that he derided it as spooky. The ER equals EPR conjecture offers a potential geometric explanation for this spookiness. It posits that these two entangled particles are not actually communicating faster than light across a vast, empty space. Instead, they are connected by a microscopic, Planck-scale wormhole, a tiny, tunnel-like shortcut through the fabric of spacetime itself. The particles aren't sending a signal, they are, in a very real geometric sense, right next to each other, linked by a hidden bridge. This provides a beautiful, visual way to understand entanglement not as magic, but as a physical connection woven into the very geometry of the universe, a connection that is simply too small for us to perceive directly. The implications of this idea become truly transformative when we apply it to black holes and the information paradox. Consider the puzzle of what happens to information that falls into a black hole. According to traditional thinking, it crosses the event horizon and is lost forever, leading to the paradox when the black hole evaporates. But ER equals EPR offers a radical way out. Imagine two black holes that are quantum entangled with each other. The conjecture suggests that these two black holes would not be separate entities. They would be connected by a giant, traversable wormhole, a kind of cosmic subway tunnel. Now the most mind-bending part, this configuration could be equivalent to a pair of entangled particles, but on a macroscopic scale. If you throw a piece of information into one of these entangled black holes, where does it go? The conjecture implies it doesn't simply vanish into the singularity of the first black hole. Instead, because the two black holes are connected by the wormhole, the information instantly travels through this bridge and emerges from the second black hole. From the outside perspective, the information never actually entered the first black hole in the traditional, isolated sense. It simply used the black hole as a portal, transferring itself to its entangled partner. In this picture, the information is never truly lost behind a horizon, neatly sidestepping the core of the information paradox. This perspective fundamentally redefines our view of spacetime. It hints that the strange, non-local connections of quantum entanglement might be the very threads that stitch the fabric of space and time together. What we perceive as empty, continuous space could, at its most fundamental level, be a complex network of countless microscopic wormholes linking every quantum of the universe. Space itself might be built from entanglement. This is a concept that turns physics on its head, suggesting that gravity and the geometry of spacetime are not the primary realities, but rather emergent phenomena that arise from a vast, underlying quantum web of connections. While ER equals EPR is still a conjecture, a powerful and compelling idea rather than a proven theory, it represents one of the most promising and exciting paths toward unifying general relativity and quantum mechanics. It provides a concrete, geometric language to describe how the universe might operate at its deepest level, transforming the spooky action at a distance into an elegant dance of spacetime geometry. Yet, for all their terrifying complexity, black holes have long been thought to possess a strange and elegant simplicity. This is the essence of the no-hair theorem, a cornerstone of classical general relativity. In the world of Einstein's theory, a black hole is the ultimate minimalist object. No matter how intricate, messy, or richly structured the star or gas cloud was before its collapse, the resulting black hole is stripped down to just three bare essentials: its mass, its electric charge, and its spin or angular momentum. Everything else, every detail about the elements that formed it, the magnetic fields it possessed, the pattern of its explosion, is lost forever behind the event horizon, erased from the universe's memory. The theorem poetically declares that black holes have no hair, a metaphor meaning they have no other distinguishing features or fuzz. A billion solar mass black hole formed from a quasar and one formed from dark matter would be completely indistinguishable if they had the same mass, charge, and spin. They are celestial bald heads, revealing nothing of their turbulent past. But is this elegant simplicity too good to be true? The limits of the no-hair theorem are now being tested as never before, and the cracks are beginning to show, primarily thanks to the strange world of quantum physics. The central challenge is this: if the no-hair theorem holds absolutely, then the only information available about a black hole is out there on the event horizon, defined by its mass, charge, and spin. Yet, as we've seen, black holes also possess an immense amount of entropy, which implies a vast number of internal states. How can an object be so incredibly simple from the outside and yet so complex on the inside? This paradox suggests that something must be missing from the classical picture. Physicists now ask a tantalizing question: could quantum effects endow black holes with a subtle kind of quantum hair? The idea of quantum hair proposes that there might be ways for information about what fell into a black hole to leave a faint, quantum-level imprint on its gravitational field, an imprint that persists outside the event horizon. Imagine dipping a perfectly smooth, featureless metal ball into different types of paint. Classically, after you wipe it clean, the ball is identical every time. But with a powerful enough quantum microscope, you might still detect a few residual molecules of pigment clinging to its surface, betraying which color it was dipped in. In a similar vein, quantum hair suggests that certain properties of the original matter, perhaps related to fundamental quantum fields, could bleed through the horizon via subtle gravitational effects, creating a unique signature in the spacetime around the black hole. This wouldn't be a classical feature you could see, but a tiny, measurable deviation in how the black hole warps space and interacts with other particles. It would mean that black holes are not perfectly bald, they have a delicate quantum fuzz. This leads to the possibility of hidden structures or fields that somehow survive the violent collapse. While classical fields like magnetism are thought to be swallowed, what about more exotic entities? Could there be a persistent, large-scale magnetic field that is somehow anchored not in the matter itself, which is gone, but in the twisted geometry of the spacetime around the rotating black hole? Or what about hypothetical fields from theories beyond the standard model, like actions or other ultra-weak fields? These might not be eradicated by the collapse, but could instead configure themselves around the newborn black hole, creating a unique hairstyle that depends on what formed it. The interior may be a chaotic mess leading to a singularity, but the external gravitational and field environment might still carry a fossil record of its birth. Testing these ideas is no longer just a theoretical exercise, it is the primary mission of a new era of astronomy. The direct detection of gravitational waves has given us a powerful tool to probe the very nature of black holes. When two black holes spiral together and merge, the resulting single black hole rings down, vibrating like a struck bell as it settles into its final, simple state. The frequencies and decay rates of these gravitational waves are a direct probe of the object's structure. According to the no-hair theorem, the ring down should be composed of a very specific set of tones determined only by the final mass and spin. But if the black hole has any hidden quantum structure or external fields, it would ring with additional, unexpected frequencies. By carefully listening to the gravitational wave chiming of these cosmic bells with observatories like LIGO and Virgo, scientists are actively searching for these anomalous tones. Finding them would be a monumental discovery, shattering the classical no-hair theorem and providing the first direct evidence that black holes are far more complex and far more interesting than Einstein ever dreamed. It would open a direct window into the quantum nature of gravity and finally tell us what these dark giants are truly made of. We've explored the bizarre possibility of firewalls and wrestled with the question of what lies inside a black hole, but all of these ideas rest on a surprisingly fragile foundation: the stability of the event horizon itself. For decades, our picture of this boundary has been stark and absolute, a mathematically perfect one-way membrane from which nothing, not even light, can return. It's the ultimate point of no return, a silent and unmoving edge to the known universe. But what if this perfect barrier isn't so perfect after all? What if the event horizon is not a static, eternal wall, but a dynamic surface that can flicker, fluctuate, or even dissolve under the right conditions? This is the next profound mystery, one that challenges the very definition of a black hole and forces us to ask whether the horizon's perfect stability is merely an illusion created by our incomplete theories. The classical equations of Einstein's general relativity paint a beautifully smooth and stable picture. In this view, once an event horizon forms, it is a permanent fixture of spacetime, an invisible sphere that simply grows as more matter falls in. It's a one-way street carved into the fabric of the cosmos. However, this perfect picture begins to fray when we introduce the chaotic rules of quantum mechanics. In the quantum world, nothing is ever perfectly still or certain. The Heisenberg uncertainty principle tells us that at the tiniest scales, there is a fundamental fuzziness to reality. Energy and time are linked in such a way that empty space is never truly empty. It is a seething sea of virtual particles popping in and out of existence. We already know this quantum jitter is responsible for Hawking radiation, but could it also affect the event horizon itself? Some theorists suggest that this constant quantum foam must cause the horizon to fluctuate. Instead of being a sharp, definite boundary, the true event horizon might be a blurry, quantum mechanical surface, jittering and roiling like the surface of a boiling pot of water. At any given instant, the precise location of the point of no return might be slightly ambiguous, a statistical average rather than an absolute line in the sand. This idea of a fluctuating horizon opens the door to even more dramatic possibilities. Could these quantum fluctuations become so violent that they tear the horizon apart entirely? One compelling line of thought comes from the study of black holes that are nearly, but not quite, extremal. An extremal black hole is one that has the maximum possible charge or spin for its mass, a theoretical limit where the event horizon's properties become peculiar. As a black hole approaches this extreme state, the inner and outer event horizons move closer together. In the perfect mathematical limit, they would merge, and the event horizon would effectively vanish, exposing the singularity and creating a naked singularity. While the cosmic censorship hypothesis suggests nature forbids this, the quantum journey toward that limit is fraught with instability. The intense energies and fields near an almost extremal black hole could amplify quantum effects, potentially causing the horizon to become a turbulent and volatile region. In such a state, the horizon might not be a clean barrier, but a temporary and dynamic structure, perhaps even flickering in and out of existence. This has a breathtaking implication. If the horizon is not permanently stable, then the black hole itself might not be a permanent object. Imagine a scenario where quantum gravitational effects, which we don't yet fully understand, cause a profound phase transition in spacetime. Just as heating liquid water transforms it into a gas, perhaps under certain extreme conditions, the very fabric of spacetime that constitutes the event horizon could undergo a similar transition, dissolving the horizon and revealing what lies within. This isn't science fiction, it's a serious, albeit highly speculative, area of theoretical research. If such an event were possible, even for a fleeting moment, it would mean that the interior of a black hole is not forever sealed. Information that fell in could, in principle, leak back out, not through the slow trickle of Hawking radiation, but in a sudden, catastrophic eruption if the horizon were to destabilize. The stability of the event horizon is therefore not just a technical detail. It is the linchpin holding together our entire classical understanding of black holes. If the horizon is fundamentally quantum and unstable, then many of our cherished paradoxes might be resolved or at least transformed. The information paradox, for instance, becomes far less paradoxical if the horizon is a leaky, fluctuating membrane rather than a perfect prison wall. Matter falling in might not be forever lost, but merely trapped behind a temporary barrier that occasionally develops cracks. The terrifying finality of the event horizon, a concept that has captured the human imagination for decades, might be an approximation, a useful fiction that breaks down when we finally marry gravity with the quantum world. The quest to understand the horizon's true nature is a direct assault on the heart of the black hole mystery, probing whether its most famous feature is a permanent monument or a fragile illusion, waiting for the right physics to make it vanish. But everything we've discussed so far rests on a single, monumental assumption that the dark, incredibly massive objects we observe at the centers of galaxies and in binary systems are, without question, the black holes predicted by general relativity. What if we've been misidentifying the universe's most enigmatic objects? This brings us to a fascinating and radical possibility, that some of these cosmic dark spots are not black holes at all, but something even stranger. We're entering the realm of ultra-compact exotic objects, theoretical entities that mimic the gravitational pull and darkness of a black hole, but are built from entirely different and unexpected physics, lacking both an event horizon and a crushing singularity. One of the most compelling of these hypothetical objects is the gravastar, short for gravitational vacuum star. Imagine a black hole, but instead of a one-way event horizon leading to a point of infinite density, the gravastar presents a thin, physical shell of ultra-dense matter. This shell is what we perceive from the outside, and it's so incredibly massive that it bends light almost identically to an event horizon, creating a similar shadow. But here's the profound difference. Inside this shell, the gravastar is not empty space leading to a singularity. Theorists propose that the interior is a bizarre region of dark energy, the same repulsive force driving the acceleration of our universe. In this picture, the immense gravitational collapse of a dying star is halted at the last possible moment by a phase transition, where the ordinary matter transforms into this exotic, dark energy core. The gravitational pull from the dense shell is balanced by the powerful negative pressure pushing outward from the dark energy within, creating a stable, static object that looks like a black hole from a distance, but has no point of no return and no central singularity to break the laws of physics. Another captivating candidate is the boson star. Unlike normal stars, which are powered by nuclear fusion and composed of particles like protons and electrons, a boson star would be a gigantic, diffuse sphere made entirely of light, stable particles known as bosons. Think of the Higgs boson, for instance, or theoretical particles like actions. These bosons, governed by the rules of quantum mechanics, could collectively form a giant coherent wave, a single quantum state on an astronomical scale, held together by its own gravity. Depending on the mass and type of the boson, such a star could collapse under gravity to an incredibly small size, becoming so dense that it also traps light and creates a shadow nearly identical to a black hole's. Yet, because it's a quantum wave, it would have no sharp surface and, crucially, no event horizon. Light would struggle immensely to escape, but given enough time and the right conditions, some photons could still leak out, unlike from a true black hole. A boson star is essentially a ghostly, giant atom, a single quantum object shining faintly with a mass potentially millions of times that of our Sun. So, if these exotic objects can perfectly mimic black holes in terms of their gravity and darkness, how can we possibly tell them apart? This is where our new astronomical tools become absolutely essential. Gravitational wave observatories like LIGO and Virgo are not just listening for the collision of black holes, they are listening for the subtle telltale signs of what these objects actually are. When two black holes merge, the event horizons of the two objects plow into each other, and the resulting single black hole rings down in a very clean, specific way. But if the colliding objects were something else, like two gravastars, the merger would be dramatically different. There would be no clean event horizon merger. Instead, the dense shells of the gravastars would physically smash into each other, creating a much more complex and messy gravitational wave signal, with extra wiggles and vibrations both during and after the collision. Furthermore, a boson star merger would be even more distinct. Because boson stars are diffuse quantum objects, they would likely not merge instantly but might pass through each other, creating a series of repeated gravitational wave bursts before finally coalescing. Perhaps the most promising test comes from the Event Horizon Telescope and its groundbreaking image of the black hole shadow in the galaxy M87. That dark silhouette surrounded by a bright ring of light is what general relativity predicts for a black hole's event horizon. But what would a gravastar look like? While it would also cast a dark shadow, the absence of a true event horizon and the presence of a physical surface could create subtle differences in the sharpness of the shadow's edge or the brightness of the surrounding ring. A boson star, being a transparent quantum wave, might not create a perfectly dark shadow at all, but rather a fuzzy, grayish region where some light manages to escape. As the resolution of these telescopes improves, they will be able to scrutinize these shadows in exquisite detail, looking for any deviation from the perfect black hole prediction. The ultimate goal is to catch one of these cosmic imposters in the act, to find a dark, massive object that, upon closer inspection, reveals itself to be something entirely new, a doorway not to a singularity, but to a new chapter in fundamental physics. Shifting our focus from the nature of singular black holes, we encounter a dramatic cosmic process on an entirely different scale, the spectacular collision of entire galaxies and the supermassive black holes that anchor them. When two galaxies are drawn together by gravity, their central black holes are destined to meet, beginning a slow, gravitational dance that should culminate in a cataclysmic merger. This process is fundamental to how galaxies grow and evolve, and we see evidence of these binary black hole pairs throughout the universe. Yet, a stubborn mystery known as the final parsec problem threatens to halt this cosmic tango in its final stages, leaving these colossal objects in a seemingly eternal standoff. The problem begins as the two black holes, having been brought together by the merger of their host galaxies, spiral inward. They lose energy through a process called dynamical friction, where their gravity slingshots surrounding stars, effectively creating a gravitational drag that slows them down. This works beautifully until the black holes get to within roughly 1 parsec of each other, a distance of about 3.26 light-years. At this separation, they have effectively cleared out a hollow in the stellar core of the new galaxy. They've ejected or flung away most of the stars that were on orbits that could interact with them and steal their orbital energy. With no more stars to efficiently rob them of momentum, the black holes should stall. They would become a stable, long-lived binary system, forever circling each other without ever getting close enough for their gravitational fields to take over and seal the deal. This presents a major contradiction for our models of galactic evolution. We observe the powerful gravitational waves from mergers of stellar mass black holes, proving that such cosmic unions do happen. For supermassive black holes to merge and produce the universe-shaking ripples we expect to detect with future observatories, they must find a way to solve this final parsec problem. If they don't, our understanding of how the most massive structures in the universe form is fundamentally incomplete. So, how do they bridge this final, critical gap? Theorists have proposed several ingenious mechanisms, each turning the galactic core into a more dynamic and crowded environment than we might have imagined. One leading solution involves a third black hole, flung into the mix by a subsequent galaxy merger. A triple black hole system is inherently unstable. The complex gravitational interactions between the three objects can lead to a spectacular gravitational slingshot, where one of the black holes is ejected at tremendous speed, recoiling and carrying away the excess energy and allowing the remaining two to plunge together. It's a chaotic, celestial game of gravitational billiards that could provide the necessary kick to overcome the stalemate. Another compelling possibility is that the binary black holes are not orbiting in a perfect vacuum, but are instead embedded in a vast, swirling reservoir of gas, the leftover material from the galactic collision. As the black holes orbit, they plow through this dense gas, creating spiral-shaped density waves. These waves act like a constant brake, sapping the orbital energy of the binary and causing them to spiral inexorably closer. The friction from this gaseous disk could be the steady hand that guides them across the final parsec, pushing them into the regime where gravitational wave emission becomes the dominant force and the final, rapid in-spiral begins. There's also the role of the countless stars that remain, albeit on wider orbits. While the black holes may have cleared their immediate vicinity, a continuous supply of stars on chaotic, centipede-like orbits could be funneled into the binary's grasp over millions of years. Each stellar flyby transfers a tiny amount of energy away from the black holes, and over astronomical timescales, this steady trickle of interactions could be enough to solve the problem. The final parsec problem forces us to see a galactic core not as a static environment, but as a constantly churning system where gas, stars, and even other black holes all play a part in orchestrating the ultimate cosmic merger. The solution is likely a combination of these mechanisms, varying from galaxy to galaxy, and finding the definitive answer is crucial for piecing together the complete life story of the universe's largest black holes and the galaxies they rule. Now, let's tune our instruments to a different kind of cosmic signal, one that doesn't come from the violent collisions of black holes, but from the steady, luminous rain of matter spiraling into them. When astronomers point their telescopes at an active black hole, they don't see a static, steady light. Instead, they often detect a fascinating and intricate flickering, a rapid fire dance of brightness changes in the X-ray light coming from the superheated gas in the accretion disk. This isn't random noise. Hidden within this chaotic twinkling are distinct, repeating patterns known as quasi-periodic oscillations, or QPO. Think of it as a cosmic drumbeat, a rhythmic pulse buried in the roar of the inferno. The quasi part is crucial. It means the rhythm is almost, but not perfectly, periodic. It's like a drummer with an incredibly steady, yet slightly wavering tempo. These QPOs are not just a curiosity, they are a rich source of information, a secret code emanating from the very edge of the event horizon, and deciphering this code has become one of the most active and challenging pursuits in high-energy astrophysics. The central mystery is straightforward yet profound. What physical mechanism in this incredibly extreme environment is acting as the drum, and what is causing it to beat? The accretion disk around a black hole is a maelstrom of forces, where gas is heated to millions of degrees as it is stretched and squeezed by immense tidal gravity. Any slight instability in this flow can create oscillations, but the QPOs we see are too coherent and too stable to be caused by simple turbulence. They must be the signature of a fundamental, structured process happening in the most violent region of spacetime. The leading theories all point to key locations and properties of the black hole itself. One of the most important concepts here is the innermost stable circular orbit, often called the ISCO. This is the closest point to the black hole where matter can still orbit in a stable circle. Any closer, and the fabric of spacetime becomes so steep that matter plunges inexorably inward, crossing the event horizon in a final, silent freefall. This orbit acts like a hard edge, a cosmic cliff. Theorists suggest that the inner rim of the accretion disk, as it bumps up against this cliff, could oscillate or precess, much like a warped record wobbling as it spins. This wobble, happening dozens or even hundreds of times per second, could modulate the X-ray light we see, creating a clear, rhythmic QPO. If this is true, then simply by measuring the frequency of this oscillation, we could directly measure the size of the ISCO, which is itself determined by the black hole's mass and spin. It would be like using the pitch of a tuning fork to determine its dimensions. Another compelling idea ties the QPOs directly to the spin of the black hole through a phenomenon known as frame dragging. According to general relativity, a rotating black hole doesn't just warp space, it twists it, dragging the very fabric of spacetime around with it like a cosmic whirlpool. This effect is strongest in a region just outside the event horizon called the ergosphere. Matter in the accretion disk caught in this dragged spacetime might be forced to orbit at specific resonant frequencies, like a bell that only rings at certain pure tones. In this model, the QPOs are the ringing of spacetime itself, a direct sonic imprint of the black hole's rotation. A faster spin would produce a higher frequency ring, giving us a potential direct measurement of one of the black hole's most fundamental properties. A third major theory suggests the oscillations are caused by instabilities within the accretion disk itself, where sections of the flow resonate, building up pressure and releasing it in a rhythmic flash. Magnetic fields, which are thought to be incredibly powerful and tangled in this region, could also play a role, snapping and reconnecting in a periodic rhythm that heats the gas and creates the observed flashes of X-rays. The truth is that these mechanisms are not mutually exclusive. Multiple types of QPOs are often seen from the same black hole, suggesting a whole orchestra of different instruments, resonances, precession, and magnetic storms, all playing together in the final moments before matter vanishes from our universe. Solving the mystery of QPOs is not just an academic exercise, it represents a potential revolution in how we measure black holes. Currently, determining the mass and spin of a black hole is a difficult, multi-step process that often relies on indirect methods and complex modeling. If we can confidently link QPO frequencies to the innermost stable circular orbit or the frame dragging rate, they would become a direct and powerful tool, a cosmic seismometer for probing the fundamental nature of spacetime. By simply listening to the rhythmic flicker of X-rays, we could weigh a black hole and clock its spin with unprecedented precision. This would open a new window into the population of black holes across the universe, allowing us to understand their evolution and demographics in a completely new way. For now, the quasi-periodic oscillation remains a tantalizing, unsolved rhythm, a beat from the edge of oblivion that holds the key to mapping the invisible geometry of the most extreme objects in the cosmos. From the rhythmic flicker of quasi-periodic oscillations, we now turn to one of the most visually spectacular and energetically staggering phenomena in the entire cosmos, the relativistic jet. Picture this: from the poles of a supermassive black hole, a beam of incandescent plasma, a fire hose of matter and energy, erupts outward. It's not a gentle diffusion, it's a tightly focused spear stretching for thousands, even millions, of light years across intergalactic space, all while moving at a breathtaking 99.9% of the speed of light. These are not mere streams of light, They are veritable monsters of power capable of punching through entire galaxies, influencing the formation of stars and reshaping the destiny of the space they inhabit. We observe these colossal structures emanating from active galactic nuclei and even from smaller stellar mass black holes in our own galaxy. The raw power involved is almost inconceivable, often exceeding the combined output of every star in the galaxy that hosts them. While we have identified the key ingredients in this cosmic engine, a spinning black hole, a swirling accretion disk, and immensely powerful magnetic fields, the precise recipe, the exact step-by-step process that takes this chaotic, swirling chaos and forges it into a blade of pure energy, remains one of the most compelling and unresolved puzzles in all of high-energy astrophysics. Think about the sheer engineering challenge this presents. To create such a jet, you must solve three distinct but interconnected problems: launch, collimation, and power. Launching is the initial act of lifting material from the accretion disk, a pancake of superheated gas orbiting the black hole and propelling it upward from the poles. This is no small feat against the black hole's immense gravitational pull. Then there's collimation, the process of taking that erupted material and squeezing it, focusing it into an incredibly narrow, pencil-thin beam that doesn't fan out and dissipate over astronomical distances. Finally, there's the question of power. Where does the energy come from to accelerate particles to such ludicrous speeds? The gravitational potential energy released by matter falling inward is colossal, but converting that energy efficiently into a directed outward blast requires a mechanism of unbelievable precision and force. It's like trying to build a rocket engine in the heart of a hurricane, using only the storm's own turbulence as fuel and construction material. The leading theory for this entire process is a magnificent interplay between the black hole's spin and magnetism, often referred to as the Blandford-Zeenagic mechanism. The key player here is the black hole's ergosphere, that region just outside the event horizon where spacetime itself is dragged around by the black hole's rotation. Imagine the black hole as a spinning sphere dipped in a vat of magnetic field lines. These lines are anchored in the ionized, swirling plasma of the accretion disk. As spacetime is whirled around in the ergosphere, it twists these magnetic field lines into an incredibly tight, powerful coil. This rotating magnetic field acts like a giant slingshot or a cosmic electric generator, creating intense voltages that rip charged particles from the accretion disk and fling them outward along the black hole's rotational axis, the path of least resistance. In this model, the rotational energy of the black hole itself is being tapped and converted directly into the jet's kinetic energy. It's an engine that runs on stolen spin, slowly breaking the black hole's rotation to power a beacon visible across the universe. Yet, the Blandford-Zeenagic mechanism, while elegant, is likely not the whole story. An alternative or perhaps complementary process, known as the Blandford-Payne mechanism, focuses its attention on the accretion disk itself. In this scenario, the disk acts like a giant winch. The intensely magnetized, rotating plasma in the inner disk can fling material outward, much like a sling. As gas from the disk is tied to these magnetic field lines, the rapid rotation of the disk flings it centrifugally upward. The magnetic fields then act as a guide, channeling this flung material into the polar regions and helping to collimate it into a tight beam. It's possible that both mechanisms operate in tandem, with the black hole's spin providing the ultimate power source through Blandford-Zeenagic, while the accretion disk contributes mass and additional magnetic structuring through the Blandford-Payne process. The balance between them might depend on the specific black hole, its rate of spin, how much it's feeding, and the configuration of its magnetic fields. However, even with these powerful theoretical frameworks, the devil is in the details, and the details are ferociously complex. How, for instance, is the jet initially launched from a region of such incredible density and turbulence? How do the magnetic fields remain so incredibly ordered and strong amidst the chaos to keep the beam focused over millions of light years? The process of collimation is particularly tricky. Some models suggest that the pressure from the surrounding accretion disk and a slower moving wind of particles from the disk itself act like a nozzle, squeezing the faster central jet and keeping it narrow. It's analogous to putting your thumb over the end of a garden hose to create a tighter, more forceful stream, but the scales and forces involved are astronomically more extreme. Furthermore, we see jets that are knotty and show bright spots where internal shocks occur, as faster-moving material plows into slower-moving clumps within the jet itself. This tells us the flow is not perfectly smooth, but a dynamic and violent internal struggle, all happening at relativistic speeds. Unraveling the exact sequence of events, from the particle's plunge toward the event horizon to its ultimate ejection in a beam of raw power, requires us to understand plasma physics and general relativity in conditions we cannot hope to recreate on Earth, pushing our computational models and our very understanding of physics to their absolute limits. But for all their immense gravitational power, black holes still only account for a tiny fraction of the universe's total mass. The real heavyweight, the true ghost in the cosmic machine, is dark matter, an invisible substance that outweighs normal matter 5 to 1. For decades, these two cosmic enigmas have been studied in separate silos. But what if they are secretly connected? What if the key to understanding dark matter lies not in some exotic, undiscovered particle, but in the very first black holes to ever form? This is the tantalizing possibility that black holes themselves, a specific kind from the dawn of time, could be the dark matter we've been searching for. The idea centers on primordial black holes. Unlike the stellar mass black holes formed from dying stars or the supermassive ones at galactic centers, primordial black holes are theorized to have been forged in the extreme density and pressure of the universe's very first moments, less than a second after the Big Bang. Tiny random fluctuations in that seething, primordial soup could have been so intense that pockets of space directly collapsed under their own weight, creating black holes of all sizes, from smaller than an atom to many times the mass of our Sun. If vast numbers of these primordial black holes were created, and if a specific mass range of them has survived to the present day, they could be floating unseen throughout every galaxy, including our own Milky Way, providing the gravitational scaffolding that holds them together without emitting any light. They would be the perfect, if somewhat sinister, candidate for dark matter, massive, invisible, and only interacting with the rest of the universe through gravity. This elegant idea, however, faces a series of intense observational challenges. The universe has placed strict limits on how many such black holes can exist. If there were too many primordial black holes with the mass of a large asteroid, for instance, their collective gravitational lensing effect would have distorted the light from distant supernova in a way we simply don't see. If they were as common as dust grains, they would have left a clear imprint on the cosmic microwave background, the leftover radiation from the Big Bang. And if they were too heavy, they would have dynamically disrupted the delicate orbits of stars in fragile star clusters and the thin streams of stars that wrap around our galaxy. These observations have systematically closed the window on primordial black holes, making up 100% of dark matter across most mass ranges. Yet, a fascinating sliver of possibility remains. There is a mass window between about the mass of a large mountain and the mass of a small planet, where primordial black holes could still constitute a significant portion, perhaps even all, of the dark matter. These objects would be planet-sized in mass but compressed into a volume smaller than a single atom, making them virtually impossible to detect directly with current technology. They would drift through the galaxy like silent, invisible icebergs, and we would only notice their presence by the subtle ripples they create in the fabric of space-time itself. This leads to the other side of the connection. Even if black holes aren't made of dark matter, do they actively interact with it in a unique and detectable way? A black hole's gravity is a powerful law for all matter, dark or light. While dark matter doesn't form accretion disks and glow with heat like normal matter, because it doesn't experience electromagnetic forces and therefore doesn't collide or radiate, it is still affected by gravity. Theorists suggest that a black hole moving through the galaxy would sweep up a halo of dark matter particles, gravitationally pulling them into a dense, spike-like concentration around it. This incredibly dense cloud of dark matter could then leave a distinct fingerprint, as dark matter particles in this spike annihilate with each other. If they are the kind of particle that does such a thing, they could produce a unique burst of gamma rays, with the black hole acting as a powerful natural amplifier for this otherwise faint signal. Alternatively, the sheer density of the dark matter spike would subtly alter the gravitational waves emitted when two black holes merge. The in-spiral and ring-down would be minutely different from a merger happening in a region of low dark matter density, providing a second, independent way to probe this invisible interaction. The potential to solve two of cosmology's greatest puzzles with a single insight is what makes this connection so compelling. Finding evidence that a significant portion of dark matter is made of primordial black holes would revolutionize our understanding of the early universe, revealing a far more tumultuous and dramatic beginning than we currently envision. It would also mean that dark matter isn't an exotic new particle at all, but rather a fossil population of ancient gravitational collapses. Conversely, detecting the specific signature of a dark matter spike around a known black hole would provide the first ever indirect map of dark matter's distribution on the smallest scales and give us crucial clues about its fundamental properties. Both paths of investigation are actively underway, with astronomers using gravitational wave detectors, gamma-ray telescopes, and meticulous studies of stellar motions to hunt for these subtle cosmic clues. The black hole-dark matter connection represents a profound convergence of mysteries, a hypothesis that dares to link the darkest objects in the universe with its most dominant substance, suggesting that the solutions to our biggest questions might be hidden in the silent, gravitational dialogue between them. This journey into the holographic principle begins not with a distant galaxy or a complex equation, but with a simple, everyday object, a credit card. The strip on the back of that card is a perfect, if low-tech, hologram. Shine a light on its two-dimensional surface, and a complete three-dimensional image appears floating in space. Every detail, every bit of depth and perspective of that image is encoded on that flat, magnetic strip. Now take that concept and apply it to the entire cosmos. What if our universe, with its vast three-dimensional volume of stars, planets, and black holes, is itself a holographic projection? What if everything we see, touch, and experience is merely a translation of information stored on a distant, two-dimensional surface? This isn't science fiction. It is a serious, radical theory of physics, and its origins lie directly in the paradoxical nature of black holes. The seed for this universe-altering idea was planted when Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, its hidden information content, is not proportional to its volume as it is for every other object we know, but to the area of its event horizon. This was a stunning departure from intuition. Imagine a library. The amount of information, the number of books it can hold, is determined by its three-dimensional volume. But a black hole is different. Its information capacity is set by the two-dimensional surface area of its boundary. This bizarre fact led physicist Gerard T. Hooft and later Leonard Susskind to propose the holographic principle. They argued that if the maximum information a region of space can contain is determined by its surface area and not its volume, then perhaps all the information within that volume is actually stored or painted onto its bounding surface. For a black hole, this means that every single bit of information about every star, every atom, every book that ever fell inside is not lost in the three-dimensional singularity. Instead, it is meticulously encoded as tiny, Planck-scale ripples and vibrations on the two-dimensional canvas of the event horizon. The black hole in this view is like that credit card hologram. The three-dimensional interior we imagine is just a projection, a translation of the data written on its two-dimensional surface. This principle was dramatically solidified through the work of Juan Maldaisner, who discovered a precise mathematical realization of this idea, known as the AD-S/CFT correspondence. In this complex framework, a hypothetical universe with properties like our own, which includes gravity and is described by a string theory living in an anti-de Sitter space, is completely equivalent to a different kind of theory, a conformal field theory, that lives on its boundary, a universe with one less dimension that has no gravity at all. In this mathematical duality, every single event, every particle interaction, every gravitational wave within the bulk of the universe has a perfect, one-to-one counterpart in the physics playing out on its boundary. A star-going supernova in the three-dimensional universe might be represented by a specific, complex dance of quantum fields on the two-dimensional surface. It's as if the entire cosmic movie we are living in is being directed and produced by a cast of actors performing on a flat, lower-dimensional stage. This correspondence provides a concrete, calculable proof of concept that the holographic principle is mathematically consistent and could be a genuine property of our reality. The implications of this for our understanding of space-time and information are nothing short of revolutionary. First, it offers a breathtakingly elegant solution to the black hole information paradox. If the information of infalling matter is never truly lost into a three-dimensional singularity, but is instead immediately encoded onto the event horizon surface, then it is never truly destroyed. As the black hole emits Hawking radiation, this process can be understood as a subtle, complex decoding of that surface information, translating it back into particles that escape into the wider universe. Information is preserved, quantum mechanics is saved, and the paradox dissolves, all because the three-dimensional drama of destruction was an illusion. The real story was always playing out safely on the two-dimensional boundary, but the implications reach far beyond black holes, striking at the very nature of reality itself. If the holographic principle is true for our universe, then space and time, the fundamental stage upon which all of physics plays out, are not fundamental at all. They are emergent phenomena, just as the temperature of a gas is not an intrinsic property of a single atom, but emerges from the collective motion of trillions of them. The three-dimensional continuity of space and the smooth flow of time might emerge from the complex quantum interactions of countless information bits on some vast cosmic boundary we cannot yet perceive. Our perception of a solid, three-dimensional world would be a magnificent illusion, a computational output generated by a deeper, lower-dimensional reality. This turns our intuition about the world completely inside out. We are used to thinking that more dimensions mean more room, more complexity. The holographic principle suggests the opposite. The ultimate, most fundamental description of our universe might be simpler, existing on a flat, information-rich surface at the edge of everything. The world of volume, gravity, and time that we inhabit may just be the most spectacular and convincing hologram of all. A projection whose source code is written in a language of quantum bits on the boundary of space and time. If a black hole is the universe's ultimate sink, a bottomless drain from which nothing returns, then its hypothetical twin, the white hole, is the source, a cosmic geyser from which matter and energy erupt, but into which nothing can ever enter. This concept emerges directly from the same equations of general relativity that predict black holes, specifically from the maximally extended Schwarzschild solution, which mathematically describes a complete, albeit highly idealized spacetime. In this framework, a white hole isn't a separate object you could find floating in space. It is intrinsically linked to a black hole through an Einstein-Rosen bridge or wormhole. Imagine the black hole as the entrance to a tunnel and the white hole as the exit in another part of the universe, or even in another universe entirely. While matter and light are sucked inexorably into the black hole entrance, they would be violently expelled from the white hole exit. It is a one-way street in reverse, a place of pure, relentless output where the very concept of entry is physically forbidden by the geometry of space-time itself. The critical question, of course, is whether these fantastical objects are anything more than mathematical curiosities. General relativity, in its pure, theoretical form, does not forbid them. The equations are time-symmetric, meaning they work just as well if you run the clock forward or backward. If you were to take a film of matter falling into a black hole and run it in reverse, you would see matter erupting from a white hole. This mathematical elegance, however, collides with a profound physical principle, the second law of thermodynamics, which dictates that entropy or disorder must always increase. A white hole erupting ordered, low-entropy energy into the universe appears to violate this fundamental rule. It seems to be a process that decreases the overall entropy of the cosmos, which is why many physicists argue that while white holes are mathematically possible, they are thermodynamically forbidden from ever forming in our universe. They would be as improbable as a shattered glass spontaneously reassembling itself and leaping back onto a table. This thermodynamic objection is so powerful that it has largely relegated white holes to the realm of speculation. Yet their theoretical potential is so compelling that it continues to inspire radical cosmological ideas. One of the most profound is the possibility that the Big Bang itself was a white hole event. Think about it. The Big Bang is the ultimate eruption of matter and energy from a singular, incredibly dense state, and by its very definition, nothing could have existed before to enter it. Our entire observable universe could, in this view, be the interior of a white hole that began its existence 14.8 billion years ago. This provides a potentially elegant geometric origin for everything we see, transforming the Big Bang from a mysterious starting point of time into a physical event that could have been triggered by processes in a larger meta-universe. In this breathtaking scenario, every black hole that forms in our universe might itself contain or be connected to a new white hole birthing its own separate cosmos, creating an infinite fractal of universes, each with its own potentially different physical laws. An equally mind-bending proposal links white holes to the ultimate fate of evaporating black holes. As we've discussed, Stephen Hawking's work showed that black holes slowly lose mass and eventually vanish in a final burst of radiation. But what happens at the very last instant when the black hole's mass reaches zero? The straightforward answer is that it simply disappears. However, some theorists suggest that this final evaporation might not be an end but a transformation. Perhaps the black hole doesn't vanish, but rather undergoes a quantum gravitational transition, turning inside out to become a white hole. Since the black hole has been evaporating for an unimaginably long time, this newborn white hole would be microscopic, but it would then begin to disgorge all the information and energy that had been trapped inside the original black hole back into the universe. This would offer a beautiful geometric solution to the information paradox. Information isn't lost, it's merely stored for an astronomically long time before being released through this cosmic reset. The white hole in this model is the final scream of the black hole, its death and rebirth into a new form of existence. For now, the white hole hypothesis remains one of the most tantalizing what-ifs in all of theoretical physics. No astronomical observation has ever provided clear evidence for one, and the thermodynamic arguments against their spontaneous formation are formidable. Yet they persist in the imagination of cosmologists because they represent a missing piece of the puzzle, a theoretical counterpart that completes the symmetric picture offered by Einstein's equations. They challenge our understanding of time, entropy, and the very origin of our cosmos, forcing us to consider whether the universe's most dramatic events, its beginnings and its endings might be connected through these bizarre gravitational gateways. Until we have a fully realized theory of quantum gravity, the white hole will remain a glorious specter, a symbol of the universe's unexplored potential for wonder and a reminder that for every profound cosmic truth we uncover, there may be an equally profound opposite waiting in the shadows. Now we turn our attention from the architecture of space to the flow of time itself, and a proposal from Stephen Hawking so profound it aims to protect the very sequence of cause and effect from breaking down. This is the chronology protection conjecture, a daring idea suggesting the universe has built-in safeguards to prevent time travel into the past, even if the mathematics of our theories seems to permit it. The problem begins with a feature of certain black hole solutions in general relativity, particularly the rotating Kerr black hole we discussed earlier. The intense frame dragging of a rapidly spinning singularity can, in theory, twist the fabric of spacetime so severely that it creates what are known as closed time-like curves. A time-like curve is simply the path through spacetime that any object with mass must follow. Under normal circumstances, this path always moves forward in time from the past toward the future. But in the extreme warped region near a rotating singularity, the mathematics suggests these paths could loop back on themselves, connecting the future to the past. An astronaut traveling on such a path could, in principle, embark on a journey that eventually brings them back to an event in their own past, creating the potential for the classic time travel paradoxes that have fueled science fiction for generations. Hawking looked at this theoretical possibility and found it deeply unsettling. The potential for paradoxes like the infamous grandfather paradox, where you travel back in time and prevent your own grandfather from meeting your grandmother, represents a fundamental breakdown of logic and causality. Physics relies on a coherent, linear sequence of events where causes precede effects. If time loops are physically possible, this logical foundation crumbles. Hawking's conjecture was essentially a statement of faith in the universe's inherent sanity. He didn't prove that time travel was impossible. Instead, he proposed that whenever conditions arise that could create a closed time-like curve, be it a rotating black hole, a wormhole, or some other exotic configuration, a quantum effect will always step in to prevent it. He famously argued that the laws of physics must conspire to protect history from time travelers, ensuring the past remains immutable. But what would this cosmic conspiracy look like in practice? The proposed mechanism is as dramatic as the problem it seeks to solve. Imagine trying to stabilize a wormhole, another theoretical time machine, to make it traversable. This would require threading it with a special form of matter possessing negative energy density. As you attempt to configure this exotic matter to open the past, quantum field theory predicts that virtual particles would flood into the region. The closer you get to creating a time loop, the more intense this flood becomes. The energy of these quantum fields would build to infinity, creating a runaway feedback loop that either destroys the wormhole outright or creates a singularity that blocks the path, a phenomenon known as quantum instability. In essence, the universe would rather tear apart the fabric of spacetime itself than allow a paradox to occur. It's like an overcurrent protector in an electrical circuit. When the flow of causality threatens to short-circuit, the system trips a breaker, shutting down the entire operation to prevent a catastrophic failure of reality's wiring. The chronology protection conjecture sits in a fascinating gray area between profound insight and convenient assumption. It has not been proven as a fundamental theorem of physics, and some theorists question whether it is a necessary law of nature or simply an elegant way to sidestep a deeply troubling implication of our current theories. After all, general relativity is our most successful description of gravity, and if it allows for closed time-like curves even in extreme conditions, shouldn't we take that possibility seriously? Perhaps the paradoxes themselves are the key. Some physicists exploring the post-selection model of time travel suggest that the laws of quantum mechanics could be subtly different on a closed time-like curve, acting to prevent paradoxes from ever actually happening. You could travel to the past, but any action you took would be constrained by probability to only those actions that are self-consistent. You would find yourself unable to pull the trigger in the grandfather paradox, not because of a cosmic force field, but because the quantum probabilities for that specific outcome would always be zero. Your free will would be an illusion on that journey, your path rigidly guided to ensure you never alter the timeline in a paradoxical way. This view doesn't protect chronology in Hawking's sense. It instead enforces a kind of cosmic consistency, making the universe a place where time travel is possible, but profoundly pointless for anyone hoping to change the past. The debate over chronology protection forces us to confront the very nature of time. Is the flow of time, with its unwavering arrow from past to future, a fundamental property of the cosmos, or is it, like temperature, an emergent property that arises from the statistical behavior of something more basic? Hawking's conjecture leans toward the idea that causality is a foundational pillar. If we one day discover a configuration of matter or a quantum gravitational state that genuinely allows for backward time travel, it would not only invalidate this specific conjecture, but would trigger a revolution in physics as profound as the ones initiated by relativity and quantum mechanics themselves. For now, the chronology protection conjecture stands as a guardian at the gates of time, a bold declaration that the universe we inhabit is a place where history is fixed, the future is open, and the logical sequence of cause and effect is a law that even the most powerful black holes cannot break. But this entire debate about what happens inside a black hole leads us to a far grander and more fundamental struggle, one that represents the holy grail of modern physics. This is the challenge of uniting the two great pillars of 20th century science: Einstein's general relativity, which governs the immense cosmic scale of gravity and spacetime, and quantum mechanics, which rules the bizarre and probabilistic micro-world of atoms and particles. These two theories are spectacularly successful in their own domains, but they are written in completely different languages and based on mutually incompatible principles. Where they violently collide at the very heart of a black hole, we find our 23rd great mystery. The black hole interior is not just a curious place, it is the ultimate battlefield and testing ground for any proposed theory of quantum gravity. It is here, in this region of unimaginable density and curvature, that we must ask, what does spacetime itself ultimately become? General relativity gives us a very specific and incredibly elegant picture. It describes spacetime as a smooth, continuous fabric, a stage that can be warped and curved by mass and energy, but a stage that is fundamentally classical and deterministic. If you could somehow survive the journey inside a black hole, this theory suggests that you would find this fabric becoming more and more severely curved, ultimately terminating at the singularity. But along the way, space and time would still behave as the smooth, geometric entities we know from the outside. The equations paint a picture of a predictable, if violently distorted, continuum all the way to the end. The problem, of course, is that we know this beautiful picture cannot be the whole story. The singularity is the clear signal of its own breakdown, a point where the mathematics predicts infinities that are physically nonsensical. This is where quantum mechanics must surely take over. The core of the conflict lies in the concept of determinism versus probability. In general relativity, if you know the initial state of a system, you can, in principle, predict with perfect certainty its entire future path through the curved spacetime. It's a clockwork universe. Quantum mechanics, on the other hand, is inherently probabilistic. It deals in waves of possibility and fundamental uncertainty. You can only calculate the probability of a particle being in a certain place, not its certain path. Marrying these two views requires a radical new understanding of the very stage upon which physics plays out. The leading candidate theories, string theory and loop quantum gravity, approach this monumental task from completely different directions, and the black hole interior is where their predictions are put to the ultimate test. String theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops of energy strings. Different vibrational patterns of these strings correspond to different fundamental particles, like electrons or photons. In this framework, gravity arises from a specific string vibration, the graviton. Crucially, string theory requires extra dimensions of space beyond the three we experience, all curled up at an infinitesimally small scale. When applied to a black hole, string theory offers a fascinating possibility for the interior. The theory suggests that as you approach what would have been the classical singularity, the extreme curvature could cause the very notion of a smooth spacetime to unravel. The fabric of space and time might transition into a massive tangle of strings and brains multidimensional objects governed by the theory's equations. In this view, the interior is not a smooth continuum leading to a point of infinite density, but a bustling, high-energy, stringy phase where the classical idea of a singularity is replaced by a complex quantum mechanical state. The infalling matter would be transformed into this vibrating, stringy soup, and the information it carries would be preserved within this new, non-singular configuration. For string theory, the black hole interior is a place where the geometry becomes stringy, and the smooth fabric of space-time is an emergent approximation that breaks down. Loop quantum gravity takes an even more radical approach. It doesn't propose new fundamental objects, but instead seeks to quantize space and time themselves. In this theory, space is not a smooth continuum. It is composed of tiny, discrete, indivisible units, a fabric woven from finite loops. Picture the fabric of your shirt. From a distance, it looks smooth and continuous, but up close, you see it's made of individual woven threads. Loop quantum gravity suggests spacetime is like that. These elementary loops join together to form a network of spin foam, which represents the quantum state of geometry. When this theory is applied to a black hole, it makes a stunning prediction. There is no singularity. Instead of matter being crushed into an infinite density at a point, the quantum nature of space provides a fundamental repulsive force that becomes overwhelmingly powerful at the Planck scale. As matter is compressed, it reaches a maximum possible density, and then it bounces. The interior of a black hole, in this view, could connect to another region of space-time, perhaps the interior of a white hole, or even a new, budding universe. The terrifying end predicted by classical theory is replaced by a quantum rebirth. The black hole interior becomes a bridge, a transformational region where the discrete, granular nature of space-time prevents the formation of a true singularity altogether. This theoretical clash leads to a profound and testable question about the nature of reality at its smallest scale. Is space-time ultimately smooth or frothy? The concept of quantum foam, an idea championed by John Wheeler, suggests that at the Planck scale, a distance of 10 to the negative 35 meters, the peaceful vacuum of space is anything but empty. The Heisenberg uncertainty principle would cause wild, probabilistic fluctuations in the geometry of spacetime itself. Wormholes would constantly blink in and out of existence, and the very concepts of here and there would lose their meaning. The smooth stage of general relativity would be revealed as an average, a statistical illusion, much like the smooth surface of water is an illusion created by the chaotic motion of countless molecules. Inside a black hole where energies and curvatures are extreme, this quantum foam might not be a microscopic subtlety. It could be the dominant feature of reality. The interior could be a turbulent, seething sea of topology change, where the classical path of an infalling astronaut dissolves into a probabilistic cloud of potential geometries. It would be a realm where cause and effect become fuzzy, and the very sequential order of events could be scrambled. The challenge, and thus the mystery, is that we currently have no way to peer inside a black hole and observe which of these pictures, the smooth stringy phase, the discrete bouncing geometry, or the chaotic quantum foam, is correct. These theories are largely mathematical constructs, and the energies required to test them directly are far beyond anything we can create in a particle accelerator. However, the quest to solve this mystery is driving the entire field of theoretical physics forward. It forces us to ask the deepest possible questions about the nature of reality. Is space a fundamental background, or is it an emergent property? Is time a true continuum, or does it too have a smallest possible unit? The black hole interior, forever hidden from our direct view, holds the answers. It is the universe's most stringent and unforgiving exam, and any theory that hopes to be a true theory of everything must first and foremost provide a coherent, non-paradoxical, and testable description of what happens within its dark gravitational embrace. Until we pass that exam, the true quantum nature of the black hole's heart will remain one of the most significant and exhilarating unsolved problems in all of science. If the classical singularity is the universe's ultimate dead end, then the concept of the Planck star is a breathtaking proposal for a cosmic U-turn. Imagine the final, catastrophic collapse of a massive star. Instead of matter being crushed into an infinitely dense point of no return, something remarkable happens. According to the principles of loop quantum gravity, space itself is not smooth and continuous, but rather woven from a fabric of tiny, discrete, indivisible units. Think of it like a digital image on a massive screen. From a distance, the picture looks perfectly smooth, but if you zoom in to the absolute maximum, you see it's made of individual pixels. In the universe, these fundamental pixels of space are measured by the Planck length, an almost unimaginably small scale. As matter collapses inward, it compresses space to this ultimate limit. But here's where the magic happens. Just as you can't compress a digital image beyond its single pixel resolution, you can't compress space beyond the Planck scale. The quantum geometry of spacetime generates an immense repulsive force, a kind of quantum pressure that becomes overwhelmingly powerful at this maximum density. The collapse doesn't end in a singularity, it halts and then it rebounds. The collapsing matter hits this quantum wall and bounces back outward. This theoretical, super-dense object at the moment of rebound is what physicists call a Planck star. It's a celestial body with the mass of a star or even a galaxy, but compressed into a volume a trillion times smaller than an atomic nucleus, held for a moment in a state of suspended animation before beginning its explosive return journey. The life cycle of a black hole in this scenario is completely rewritten. From the outside, for almost its entire existence, it would look and behave exactly like a classical black hole, complete with an event horizon. The formation, the accretion disk, the gravitational pull, all of it would be indistinguishable from the predictions of Einstein's theory. The entire dramatic bounce happens deep inside, hidden from our view behind the event horizon. The black hole in this picture has a secret interior life. The collapsing matter forms the Planck star at the core, and the rebound begins immediately. However, because the interior of a black hole is so severely warped, time is drastically dilated. Due to the incredible gravitational time dilation predicted by general relativity, the bounce would appear from our perspective outside the event horizon to take an incredibly long time. For a stellar mass black hole, the entire process of collapse and rebound might seem to stretch out over billions or even trillions of years. The black hole would appear stable for an epoch, but it would not be eternal. The final act of this cosmic drama would be the eventual disappearance of the event horizon. When the rebounding matter from the Planck star core finally pushes its way back out to the location of the original event horizon, the horizon would simply vanish. What was once a black hole would suddenly and violently transform into a brilliant, expanding fireball of high-energy radiation and particles. essentially turning into a white hole for a brief, spectacular instant before dispersing its contents back into the universe. This provides a stunningly elegant potential solution to the information paradox. If the black hole ultimately explodes and releases all the matter and energy that fell into it, then the information is never truly lost. It was merely stored for an astronomically long time before being faithfully returned. But how could we possibly test such a mind-bending idea? We can't send a probe inside a black hole, and waiting trillions of years to see one explode isn't exactly practical. The key to testing the Planck star hypothesis lies in the very early universe and the ghostly echoes of the Big Bang. If primordial black holes were created in the intense density of the first moments of the cosmos, some of the smaller ones would be reaching the end of their lifespan and exploding right now. A stellar mass black hole would take an unimaginably long time to evaporate via Hawking radiation or to rebound as a Planck star. But a much smaller primordial black hole, with the mass of a mountain or an asteroid compressed into a microscopic volume, could have a lifespan that is short enough to fit within the current age of the universe. The rebound of such a tiny black hole would release an absolutely colossal amount of energy in a flash of high-energy gamma rays. Astronomers are actively scanning the skies for such unexplained, intense bursts of gamma radiation that cannot be accounted for by more conventional sources like supernova or neutron star mergers. Detecting a gamma ray burst with a specific signature that matches the predicted explosion of a Planck star would be revolutionary, providing the first direct experimental evidence for loop quantum gravity and fundamentally altering our understanding of black hole fate. This concept also opens up a profound connection to the origin of our entire cosmos. The Big Bang itself, in the classical model, is a singularity, the ultimate beginning where the laws of physics break down. But if a collapsing star can bounce to form a Planck star, could the entire universe have begun the same way? This leads to the theory of the Big Bounce, a cyclical model of the universe where our expanding cosmos was preceded by a previous universe that contracted to a super-dense state, hit the Planck density barrier, and then rebounded into the Big Bang we observe. In this breathtaking cosmology, the Big Bang was not a beginning from nothing, but a transition from a previous cosmic phase. Every black hole that forms in our universe could, in this view, be the seed for a new baby universe, bubbling into existence inside its own space-time continuum, with its own Big Bang triggered by the internal Planck star bounce. The Planck star is more than just a solution to the singularity problem. It's a gateway to a new vision of cosmic life cycles, where endings are merely transformations, and the universe itself may be part of an infinite, fractal chain of cosmic rebirths, each one born from the quantum bounce at the heart of a black hole. Having journeyed through the strange physics of our own universe, from the holographic principle to the quantum bounce of a Planck star, we now arrive at perhaps the most dizzying speculation of all, the possibility that black holes are not just features within our cosmos, but are the very engines of cosmic creation, serving as gateways to a vast and infinite multiverse. This idea elevates their role from cosmic destroyers to cosmic parents, suggesting that every black hole could be a womb for a new reality, and that our own universe might be the offspring of a black hole in a much larger meta-universe. This theory, known as cosmological natural selection or the fecund universe theory, was most famously developed by physicist Lee Smolin, and it proposes a form of cosmic evolution where universes that are better at producing black holes are, by definition, more fit, as they give birth to more offspring universes. In this breathtaking vision, the chain of causality stretches back not to a single, inexplicable Big Bang, but to an endless lineage of black hole births, creating a branching tree of universes that extends infinitely into the past and future. To grasp this, consider the fate of matter at the singularity. Classical physics sees it as an end, but if we incorporate the quantum gravitational ideas of a bounce, like the Planck star we just discussed, that end transforms into a beginning. When matter is compressed to that incredible density, the known laws of physics break down. In that chaotic, primordial state, the fundamental constants of nature, the strength of gravity, the mass of an electron, the charge of a proton, could be randomly reset. It's as if the universe's rulebook is shredded and rewritten. The new universe that erupts from this bounce would therefore have its own unique set of physical laws, potentially wildly different from our own. Some of these baby universes might have gravity so weak that no stars ever form, or chemistry so unstable that no complex molecules can exist. Others, like our own, might by pure chance have the perfect Goldilocks balance of constants to allow for galaxies, stars, planets, and ultimately life. This provides a stunning, non-theological explanation for why our universe seems so finely tuned for our existence. We don't live in a specially designed cosmos. We live in one that is a successful product of a grand, cosmic evolutionary process, a universe that is particularly good at making more universes just like it. This theory naturally leads to a profound and beautiful inversion of perspective. If every black hole in our universe gives birth to a new cosmos, then what does that make our own Big Bang? From the inside, we perceive it as the ultimate beginning. But from the outside, from the perspective of that parent universe, our entire cosmic history, all 14.8 billion years of expansion, all the galaxies, all of human history, is simply the interior evolution of a single black hole. We are living inside a black hole that formed in a larger, older universe. This parent universe would have its own stars, its own galaxies, and its own black holes, each one potentially containing an entire cosmos within. This creates a fractal reality, a Russian nesting doll of universes within universes, stretching onward forever. The supermassive black hole at the center of our Milky Way isn't just a gravitational trap. It is a potential cosmic egg, incubating a new universe with its own laws and wonders, completely separate and unreachable from our own. While this is one of the most speculative ideas in all of cosmology, it is not without potential pathways for testing. The most promising lies in the specific signature of the initial bounce. If our universe was born from a black hole collapse and rebound, the precise conditions of that quantum gravitational event might have left a faint imprint on the oldest light in our sky, the cosmic microwave background. Certain anomalous patterns in this background radiation, which don't fit the standard Big Bang model, could potentially be explained by the physics of a preceding collapse. Furthermore, if this evolutionary process is real, then our universe should be optimized for black hole production. This means the distribution of black hole masses and the relative abundance of the elements needed to form them should be what we observe. Finding that our universe is, in fact, exceptionally efficient at creating black holes would be a powerful piece of circumstantial evidence in favor of the theory. The multiverse hypothesis transforms black holes from being the ultimate symbols of finality into the ultimate symbols of fertility, suggesting that death and birth are inextricably linked on the grandest of scales, and that the darkness of a black hole's heart may not be an end, but the dawning light of a new cosmic day. Yet, as we contemplate black holes birthing entire universes, we are also presented with an opportunity to find their faint, dying whispers right here in our own cosmic backyard, hidden within the most energetic particles ever observed. This brings us to a fascinating intersection of the very large and the very small, connecting the ultimate fate of the smallest black holes to a long-standing cosmic ray puzzle known as the GZK cutoff. The universe is constantly bombarded by cosmic rays, which are not rays of light but are instead high-energy atomic nuclei, protons, and heavier elements racing through space at nearly the speed of light. In the 1960s, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin calculated that there should be a natural upper limit to the energy of these particles arriving from distant corners of the cosmos. Their reasoning was based on a cosmic obstacle course. The space between galaxies is not a perfect vacuum. It is filled with the diffuse glow of the cosmic microwave background radiation, the leftover heat from the Big Bang. A proton traveling across billions of light years, if it has an energy above a certain extreme threshold around 10 to the 18th electron volts, should interact with these background photons. The collision is so powerful that it creates new particles, specifically pions, in a process that saps the proton's energy. Over a long enough journey, this process acts like a cosmic speed limit, ensuring that no protons from sources farther than about 150 million light-years should reach Earth with energies beyond this GZK cutoff. It's as if the universe has a built-in regulatory system that grinds down the most energetic travelers from distant lands. The mystery is that our detectors, like the Pierre Auger Observatory, have repeatedly spotted cosmic rays with energies far exceeding this theoretical limit. We are observing particles that, according to our understanding, should not exist. They possess energies millions of times greater than anything produced in the most powerful particle accelerators on Earth. The question is immediate and profound. What cosmic accelerators are capable of launching such incredibly energetic particles, and how are they managing to reach us without being degraded by the cosmic background radiation? The most obvious suspects are the most violent events we know of: active galactic nuclei with their relativistic jets, or perhaps supermassive black holes merging at the centers of galaxies. These are certainly powerful enough to impart such tremendous energy. However, there's a catch. For these ultra-high-energy cosmic rays to avoid the GZK suppression on their journey to us, their sources must be relatively close within our local cosmic neighborhood. Yet, when we trace the paths of these mysterious particles back across the sky, they don't seem to point clearly to any such nearby, powerful astrophysical object. It's as if invisible snipers are firing the most powerful bullets in the universe from empty, dark regions of space. This is where the fate of the smallest black holes enters the picture with an elegant and compelling proposal. Imagine a primordial black hole, one of those hypothetical relics from the Big Bang, with a mass of about 1 billion metric tons. That's roughly the mass of a small mountain, but compressed into a space 1 million times smaller than a single proton. According to Hawking's theory, such a black hole would not be a stable object. It would be a ticking time bomb, evaporating over the age of the universe and now entering the final, cataclysmic stage of its life. The evaporation process, as we've discussed, is a runaway reaction. As the black hole loses mass, its temperature soars. In the last fraction of a second of its existence, its temperature would skyrocket to over 1 billion times that of the core of our Sun, and it would release its entire remaining mass energy in a tremendous burst of high-energy radiation and particles. This final flash would be a fireball of gamma rays, quarks, gluons, and other fundamental particles, which would rapidly decay and reorganize into a shower of protons, neutrons, and gamma radiation. Crucially, the protons emitted in this final burst could easily reach energies that surpass the GZK cutoff. They are not traveling across the universe, they are being created right here in our galactic halo. Because these hypothetical primordial black holes would be distributed throughout the dark matter halo that surrounds our Milky Way, their final explosive moments would produce ultra-high-energy cosmic rays that arrive at our detectors without having to traverse the vast, attenuating distances that suppress distant sources. The empty origins of these cosmic rays would suddenly make perfect sense. They aren't coming from a distant galaxy, but from the silent, invisible death throes of ancient black holes lurking in the dark outskirts of our own galaxy. Investigating this connection is a masterstroke of indirect detection. If a significant population of these tiny, evaporating black holes exists, they would not only solve the mystery of the ultra-high-energy cosmic rays, but would also provide two monumental confirmations at once. First, it would be the first definitive, albeit indirect, evidence for Hawking radiation. We would be observing the tangible aftermath of a black hole's final evaporation, confirming a prediction that has until now been purely theoretical. Second, it would prove the existence of primordial black holes, opening a direct window into the physics of the very early universe and potentially revealing that they do, in fact, make up a portion of the dark matter that shapes our cosmos. The search is on to find the specific signature of this process. The final explosion of a primordial black hole would not only produce protons but also a flash of gamma rays and a burst of lower energy particles, creating a unique multi-messenger signal. Astronomers are correlating data from cosmic ray detectors, gamma ray telescopes, and neutrino observatories, looking for coincident events that could be the smoking gun. They are also scrutinizing the exact composition and arrival directions of the most energetic cosmic rays, searching for patterns that point to a local isotropic source, just as you would expect from a halo of dark matter objects. Solving the GZK paradox with black hole evaporation would be a stunning demonstration of cosmic connectivity, showing that the answer to one of astrophysics' great puzzles was hiding all along in the quantum gravitational death of the universe's smallest and most ancient secrets. As we've seen, the information paradox has forced physicists into a corner for decades, but the battle is far from over. In fact, recent developments have injected fresh energy and surprising new perspectives into this long-standing conflict. The central question remains as sharp as ever. If a black hole evaporates completely via Hawking radiation, what happens to the detailed quantum information of the things that fell inside? For years, the debate seemed stuck between three unpalatable choices. Accept that information is truly lost, which shatters quantum mechanics. Embrace the violent firewall at the event horizon, which shatters general relativity, or imagine some exotic new physics. However, a powerful new set of ideas is emerging from the application of quantum information theory and gravitational path integrals, offering a way to potentially satisfy both quantum mechanics and gravity without resorting to paradox or drama. This new approach suggests a breathtaking possibility that information escaping a black hole isn't stored right at the horizon, nor is it trapped deep inside. Instead, it's stored far away in regions that seem completely separate from the black hole, yet are mysteriously connected through the subtle architecture of quantum entanglement. The most revolutionary of these new concepts is the idea of entanglement islands. Don't let the serene name fool you. This is a radical rethinking of where and how information resides. To grasp it, we need to think about the process of calculating what's called the fine-grained entropy of the Hawking radiation. As a black hole evaporates, the radiation it emits becomes increasingly entangled with itself. But for information to be preserved, this late-time radiation must also somehow become entangled with the very first bits of radiation that left the black hole long ago. The puzzle was always how can radiation emitted today connect with radiation from the distant past? The island formula provides a stunning answer. It tells us that when we calculate the entropy of the radiation we collect now, our calculation must include, in a very specific mathematical way, a region inside the black hole's event horizon. This region, the island, is not a physical place we can access. It's a region whose quantum information is, counterintuitively, part of the description of the distant radiation system. Think of it like this. Imagine you have a book whose final chapter is missing. You can't understand the story's conclusion, but then you discover that a copy of that missing chapter exists, not in the book itself, but encoded in the library's central catalog system, which is located in another city. The island is like that distant catalog. It's a region of space-time inside the horizon, whose entanglement properties make it an essential part of the description of the radiation that's far outside. The information about what fell into the black hole isn't sitting on the horizon. It's as if it is mirrored in this island region, and through the magic of the gravitational path integral, that mirrored information becomes encoded into the escaping Hawking radiation. This leads to a profound and almost surreal picture of the evaporating black hole. In its late stages, the geometry of space-time around it undergoes a profound topological change. The island, which lies behind the event horizon, becomes quantum entangled with the radiation that has already traveled far away into the universe. Because of this intense entanglement, the island's information is no longer localized solely inside the black hole. In the language of quantum mechanics, it is simultaneously part of the description of the external radiation field. So, when the black hole finally evaporates and the island itself vanishes, the information isn't lost because it was never truly confined there in the first place. It had already been transferred via these entanglement bridges to the radiation that now permeates space. It's a solution that avoids the need for firewalls or the destruction of information by subtly redefining what we mean by inside and outside. The event horizon becomes less of a stark, impenetrable wall and more of a quantum computational surface, where the distinction between interior and exterior is blurred by the fundamental non-locality of quantum entanglement. Of course, this island paradigm is not the final word. It is the current front line in a rapidly evolving theoretical war. The calculations are immensely complex, relying on sophisticated tools from holography and quantum gravity, and they often work best in simplified, toy model universes rather than the realistic, four-dimensional spacetime we inhabit. Skeptics rightly point out that the physical mechanism for how the information actually makes the jump from the island to the radiation remains somewhat abstract, encoded in the mathematics of the path integral rather than a simple, intuitive story. Furthermore, this new framework has sparked its own set of fascinating puzzles. If islands exist, what exactly defines their boundary? Are they a general feature of quantum gravity or a specific calculational trick for black holes? The very fact that a region behind the horizon can be used to describe a system outside of it pushes us further toward the holographic view of reality, where location is not an absolute concept but depends on the quantum state and what you are trying to describe. The debate is more vibrant than ever, with new thought experiments and precise calculations emerging at a dizzying pace, each one refining, challenging, or extending the island concept. This is not a settled science. It is a living, breathing inquiry where our most fundamental ideas about space, time, and information are being stress-tested and rewritten in real time, demonstrating that even the most intractable paradoxes can yield to fresh perspectives and relentless curiosity. Moving from the theoretical edges of quantum gravity and cosmic puzzles, we arrive at a very concrete and practical challenge that astronomers face right here in our own cosmic neighborhood: the difficult task of measuring how fast a black hole is spinning. We often picture these cosmic giants as simple, dark voids, but they are dynamic objects, and their rotation or spin is one of their most fundamental properties, a direct manifestation of their angular momentum. This spin isn't a trivial detail, it's a powerhouse. It dictates the size of the innermost stable circular orbit, influences the power of relativistic jets, and holds a fossil record of the black hole's history, revealing whether it grew steadily by Chinese letter OR violently through mergers. But pinning down this number, this single value for a specific black hole, has proven to be an observational minefield, a delicate dance of inference and interpretation that takes us to the very precipice of the event horizon itself. To understand why this is so hard, you have to appreciate that we are not measuring the spin directly. We cannot see a black hole's surface, let alone watch it rotate. Instead, we are cosmic detectives, looking for subtle clues in the light emitted from the superheated maelstrom of its accretion disk. The primary tool in this investigation is X-ray astronomy, because the innermost regions of the disk, where the gravitational and rotational energies are most extreme, glow intensely in high-energy X-rays. One of the most powerful and widely used methods involves a phenomenon known as relativistic broadening of iron spectral lines. Here's how it works. Deep in the accretion disk, atoms of iron are bombarded by X-rays, causing them to fluoresce, to emit light at a very specific, characteristic energy, like a tuning fork ringing at a pure single pitch. But as this light tries to escape from the fiercely warped spacetime close to the black hole, it is subjected to the full, bizarre effects of Einstein's relativity. The intense gravity produces an extreme redshift, stretching the light to lower energies. The incredible orbital speeds of the gas, which can approach a significant fraction of the speed of light, produce a powerful Doppler effect, blue shifting light from gas moving toward us and red shifting light from gas moving away. The combined result is that the pristine, sharp emission line from the iron atoms gets smeared out, stretched into a characteristic, skewed profile that looks like a distorted, lopsided hill rather than a sharp peak. The shape and extent of this distortion are a direct probe of how close to the black hole the iron atoms can stably orbit. A rapidly spinning black hole has a much smaller innermost stable circular orbit, allowing gas to venture far deeper into the gravitational well, which in turn produces more extreme broadening of the line. By meticulously modeling the precise shape of this skewed line, astronomers can, in principle, work backwards to calculate the black hole's spin. But this is where the plot thickens, because another, seemingly independent method often comes into play, one we've touched on before: quasi-periodic oscillations, or QPO. These are the rhythmic flickers in the X-ray brightness, the cosmic drumbeats emanating from the accretion flow. Certain types of these oscillations, particularly those at high frequencies, are thought to be tied to the fundamental orbital frequencies of spacetime itself in the innermost region. One compelling model suggests that the frequency of a specific QPO is directly linked to the orbital period at the innermost stable circular orbit. Since the location of that orbit is itself determined by the black hole's spin, measuring the QPO frequency gives us another, completely independent way to clock the spin rate. It's like having two different types of stopwatches to time the same runner on the same track. In a perfect world, they should give you the same result. The problem, and the source of a great deal of scientific debate, is that these two stopwatches don't always agree. For the same black hole, the spin value derived from the broad iron line can sometimes be significantly different from the value derived from the QPO frequencies. This isn't necessarily because one method is right and the other is wrong, but rather because they are probing subtly different aspects of an incredibly complex and dynamic system. The iron line method relies on our understanding of the precise geometry of the accretion disk and the behavior of light in that region. But what if the disk is not a perfectly thin, flat pancake as in our simplest models? What if it is puffed up or warped, or if powerful magnetic fields are altering its structure? These complexities can subtly change the shape of the iron line, leading to a potentially biased spin measurement. The QPO method, on the other hand, depends on our theoretical model for what physical process is actually causing the oscillation. Is it truly the fundamental orbital frequency at the ISCO, or is it a resonance between different frequencies, or something else entirely? If our underlying model for the drum is incorrect, then our interpretation of its beat will be off. These conflicting results are not a sign of failure, but a valuable signal. They are telling us in no uncertain terms that the environment within just a few dozen miles of a black hole's event horizon is far more turbulent, magnetically dominated, and dynamically rich than our tidy textbook models can capture. We are trying to use the blunt instruments of our current theories to dissect a region where gravity, plasma physics, and magnetohydrodynamics combine in a furious, chaotic dance. The light we are analyzing has been on a harrowing journey through this maelstrom, and decoding its message requires us to untangle all of these intertwined effects simultaneously. This is the cutting edge of black hole astrophysics, not just collecting the data, but building increasingly sophisticated and realistic models that can finally reconcile the view from the iron line with the rhythm of the quasi-periodic oscillations, to hear the same story from both the light and the beat, and in doing so, to map the violent, whirling space-time at the very edge of reality. But the search for black holes isn't just about the tiny or the colossal. There's a ghostly gap in the cosmic census that has left astronomers both puzzled and fascinated. We have two well-established families, the stellar mass black holes, the remnants of dead stars, weighing in at up to about 100 times the mass of our Sun, and the supermassive giants, the million to billion solar mass behemoths that anchor the centers of galaxies. This leaves a vast and seemingly empty desert in between the realm of intermediate mass black holes, with masses ranging from a few hundred to a few 100,000 suns. For years, these objects were purely theoretical, the missing link in the black hole family tree, and their apparent absence presented a serious puzzle. Were they simply hiding, exceptionally good at staying in the shadows, or was there a more fundamental reason they were so rare, a bottleneck in the cosmic assembly line that builds the universe's largest structures? The challenge in finding them is a direct result of their nature. They are too massive to be formed from a single collapsing star through the processes we understand, yet they are too small to dominate the dynamics of an entire galactic core in a way that's easily visible from millions of light-years away. A stellar mass black hole reveals itself by violently stripping gas from a companion star, creating a bright, flickering X-ray source. A supermassive black hole betrays its presence by powering brilliant quasars or by making the stars at the galactic center whirl around an invisible, immense mass. An intermediate mass black hole, however, might be drifting in relative isolation in a globular cluster or a small dwarf galaxy, not actively feeding enough to shine brightly, and not massive enough to whip a large number of stars into a frenzied, obvious orbit. Detecting one requires catching a subtle signature, like observing the gentle, collective sway of a small group of stars moving under the influence of an unseen, concentrated gravitational anchor. It's like trying to spot a lone, quiet person in a vast, dark field by the slight movement of a few blades of grass around their feet, rather than by the beacon of a flashlight. This elusive quality makes the handful of candidate detections we have all the more thrilling and critical. Some of the most compelling evidence has come from within dense globular clusters, ancient swarms of hundreds of thousands of stars. In several of these clusters, careful tracking of stellar motions has revealed a gravitational tug that seems to emanate from a central, dark object far too heavy to be a cluster of neutron stars or stellar mass black holes. For instance, the globular cluster Omega Centauri appears to host a central dark mass of around 40,000 suns. Another promising method involves spotting the telltale flash of a tidal disruption event. When a star wanders too close to a black hole, the immense tidal forces can shred it, stretching it into a long stream of gas that then falls onto the black hole and heats up, producing a brilliant flare of light. The duration and brightness of this flare are directly related to the mass of the black hole. Several observed flares have characteristics that point squarely to an intermediate mass culprit, a black hole of a few thousand solar masses enjoying a rare and violent feast. The profound importance of finding these missing links lies in their potential to solve the supermassive black hole growth problem. How do you get from a stellar mass seed of a few dozen suns to a billion solar mass monster in less than a billion years? Growing that large that quickly through steady accretion is like trying to fill an Olympic swimming pool with a garden hose in a single afternoon. It's a tremendous challenge. Intermediate mass black holes provide a crucial stepping stone. They could be the result of those first stellar seeds merging and accreting gas within the crowded environment of a young galaxy's core. If they exist in significant numbers, they could be the building blocks that hierarchical mergers assemble into the supermassive black holes we see today. A galaxy like our own Milky Way may have swallowed dozens of dwarf galaxies in its past, each one potentially carrying its own intermediate mass black hole. These smaller black holes would then sink to the center through dynamical friction and merge, dramatically speeding up the growth process of our own central supermassive black hole, Sagittarius A star. Without this intermediate stage, the rapid formation of the earliest supermassive black holes becomes even more difficult to explain. Yet, their potential scarcity suggests that the pathway to building them might be special and difficult. Perhaps they can only form in the uniquely dense environments of the very first star clusters in the early universe, where runaway collisions between massive stars could create a single, huge black hole seed directly. Or maybe the conditions for their sustained growth are just rarely met. They might be easily ejected from their host clusters through gravitational slingshot interactions with other black holes, becoming lonely wanderers in intergalactic space before they have a chance to grow further. The ongoing hunt for these elusive objects is therefore about much more than just completing a collection. It is a direct test of our models of cosmic structure formation and black hole evolution. Every new candidate intermediate mass black hole that is confirmed is a vital piece of the puzzle, a missing link that could finally show us how the universe builds its most powerful and mysterious gravitational engines, bridging the vast evolutionary gap between the death of a star and the dawn of a galactic empire. And so we reach the final, all-encompassing mystery, one that stretches our imagination to the very limits of time itself, the ultimate fate of black holes and the cosmos they inhabit. We must now embark on a thought experiment of staggering scale, looking trillions upon trillions of years into the future, to a universe that is almost unrecognizably old, cold, and dark. In this far-flung epoch, the grand dynamic era of galaxy formation and stellar birth will be a distant, faded memory. The last stars will have long since burned out, their embers cooling into black dwarfs. The universe will be a sparse graveyard of dead stars, planets, and dark matter, all being relentlessly pulled apart by the accelerating expansion of space driven by dark energy. In this profound and silent darkness, the black holes will stand as the final monuments to a once vibrant cosmos, but even their reign is not eternal. For billions of years, these gravitational giants grew by feasting on gas, dust, and stars, but in this future, the well of available matter will have run dry. With no new material to consume, black holes will effectively stop growing. They will become isolated islands in an ever-expanding sea of nothingness. Yet, they are not completely inert. This is where Stephen Hawking's brilliant insight becomes the dominant force in their evolution. As we've discussed, black holes slowly leak energy through Hawking radiation. For a black hole with the mass of our Sun, this process is so slow that it would take 10 to the 67 years to evaporate, a number so vast it eclipses all of cosmic history to date. But in this cold, dark universe, with the background temperature plummeting to near absolute zero, the black holes will finally begin to lose mass in earnest. They will enter their long, slow twilight, glowing with an ever-increasing heat as they shrink. The stellar mass black holes will be the first to go, their evaporation a runaway process culminating in a final, brilliant flash of high-energy particles. Later, the supermassive black holes at the centers of long-dead galaxies will follow suit, their titanic mass taking correspondingly longer to dissipate, but inevitably meeting the same end. The final act of a black hole's life is not a quiet fade, but a spectacular, violent burst of radiation, a last defiant shout in the cosmic silence before vanishing completely. This leads us to the most haunting question imaginable. What is the final state of the universe when the very last black hole emits its final particle? After the last flash of Hawking radiation fades into the void, what remains? The classical picture is one of absolute desolation, a universe of profound darkness and near-perfect emptiness. The temperature of space would asymptotically approach absolute zero. All that might be left are the scattered, cold remnants of planets and dead stars, along with a sea of ultra-low-energy photons and neutrinos, all so diffuse that they are effectively undetectable. This is the heat death of the universe, a state of maximum entropy where no energy gradients exist to do any work, no processes can occur, and all change ceases. It is the ultimate thermodynamic equilibrium, a cosmic end of time where the story of the universe simply stops. But is this bleak, static void the only possible outcome? Some theoretical models suggest more exotic possibilities, born from the quantum uncertainties that govern reality at its most fundamental level. In a universe that is effectively infinite in both space and time, even an event of infinitesimally small probability becomes not just possible but inevitable. Through a phenomenon known as quantum tunneling, a random fluctuation in the perfect vacuum could, after an unimaginable duration, spontaneously give birth to a new patch of high-energy false vacuum. This tiny bubble could then inflate at speeds faster than light, triggering a new Big Bang and birthing an entirely new universe with its own laws of physics. In this cyclical or multiverse picture, the death of our cosmic epoch is not an end, but a long, dormant winter before a new spring. The empty space left behind by the last evaporating black hole becomes the fertile ground after eons of quiet for a new genesis. Another profound consideration is the role of dark energy. If the mysterious force causing the universe's accelerated expansion continues to dominate, it could lead to a fate even more dramatic than simple cold and darkness, the Big Rip. In this scenario, the repulsive force of dark energy grows so strong over time that it tears apart all bound structures, from galaxies down to atoms and even the fabric of spacetime itself. While this would likely occur long before the last black holes evaporate, it highlights that the ultimate endpoint is still tied to mysteries we have yet to solve. The final state of a universe where black holes have evaporated is inextricably linked to the nature of dark energy and the true fate of the cosmic expansion. The ultimate fate of black holes is therefore more than just the final chapter in their own life story. It is the final chapter in the story of our entire cosmos. These mysterious objects born from the death of stars are the last great structures to shine light and energy into the deepening cosmic night. Their slow evaporation via Hawking radiation is the final significant physical process in the timeline of the universe. Their disappearance marks the true end of an era, the point at which the universe transitions from a dynamic, evolving system to a static, eternal equilibrium. This mystery ties the life cycle of the most extreme gravitational phenomena directly to the ultimate destiny of all existence, forcing us to confront the very concepts of time, entropy, and the nature of nothingness itself. It is a humbling and awe-inspiring contemplation, a reminder that even the mightiest forces in the cosmos are transient, and that the final word in the universe's story may not be written in fire or ice, but in the quiet quantum whisper of a single, final particle fading into an infinite dark. And so, after this incredible voyage through 30 of the universe's most profound enigmas, we find ourselves not at an end but at a threshold. We began by staring into the terrifying heart of the singularity, a point where physics itself declares bankruptcy, and we have journeyed outward through the paradoxical fate of information, the potential for cosmic gateways, and the holographic nature of reality itself. We have seen how these dark giants are not isolated monsters but active participants in the cosmic dance, governing the growth of galaxies, birthing new universes, and whispering their secrets through the faintest ripples in space-time and the most energetic particles imaginable. This exploration reveals a truth far more magnificent than the simple idea of a cosmic vacuum cleaner. Black holes are, in fact, the universe's ultimate laboratories. They are the only places where the two great pillars of modern physics, the cosmic scale gravity of Einstein and the probabilistic microscopic world of quantum mechanics, are forced into a direct, violent confrontation. The puzzles we have unpacked, from the firewall paradox to the chirping of quasi-periodic oscillations, are not mere intellectual curiosities. They are the precise cracks in our understanding where a new, grander theory of reality will eventually emerge. The most exciting part of this entire journey is that it is happening right now. This is not settled history. It is a living, breathing frontier of human knowledge. The equations being scribbled on whiteboards today, the data pouring in from the Event Horizon Telescope, LIGO, and gravitational wave observatories around the world, any one of these could be the key that unlocks the next great revelation. The detection of a single, unexpected gravitational wave signal, a peculiar flicker in an X-ray binary, or a theoretical insight into the quantum nature of space-time could, in an instant, solve the information paradox, confirm the existence of wormholes, or reveal the true face of the multiverse. We are living in the golden age of discovery for these cosmic mysteries, and you have a front row seat. This conversation is far from over, and your curiosity is a vital part of it. The questions that captivate you personally are the very fuel that drives science forward, so we want to hear from you. As you reflect on these 30 mysteries, which one captured your imagination the most? Does the sheer, mind-bending finality of the singularity haunt your thoughts, or are you drawn to the elegant, holographic solution to the information paradox? Perhaps the audacious idea that our entire universe resides within a black hole, or the poetic vision of a Planck star bouncing into a new creation, is what sets your mind ablaze. Let us know in the comments below. Sharing your wonder is how we build a community of cosmic explorers. If you want to continue this journey with us, delving into the wonders of quantum mechanics, the secrets of dark matter, or the next great mysteries of the cosmos, be sure to subscribe. Together, we will keep looking into the darkness, not with fear, but with the unshakable belief that every question we ask brings us one step closer to understanding the spectacular, beautiful, and deeply strange universe